So let's begin. The first speaker of the day is Niels, who is going to present us his talk. Niels.
Thanks. I went through the effort of making some transparencies, which I hope appear. And I sent them before 9. How do I change transparencies? Okay. Okay, it's very professional. I can even see here. Yeah, okay. Thanks. It's a great pleasure to be here, and fantastic that Cost, under the heading of Alessandro, put together this great meeting. So I'm going to talk about non-Lorentzian geometry in different branches of physics, field theory, gravity, and string theory. It's based on work with a whole bunch of people. Could have been more of those here, but yeah. If you look at all the names, there's one person here, Jan de Boer, who gave a talk yesterday. So actually there has been quite some progress recently in understanding non-relativistic corners of field theory, gravity, and string theory. And actually, maybe just a word on the word non-relativistic, because it's a little confusing. But I try to, in this talk, when I say non-relativistic, I mean really the Galilean limit that you know from classical mechanics, so speed of light to infinity. And when I say non-Lorentzian, I mean something more general that I hope will become clear in this world. So that's why I say non-relativistic, non-Lorentzian. And this progress builds on improved understanding of underlying geometrical framework, non-Lorentzian geometries. And I hope to make clear in this talk the basics of what a non-Lorentzian geometry is. It's essentially space-times that have local symmetries other than Lorentz symmetry. And non-Lorentzian geometries have, just to give you a watch list, up front appeared in boundary geometries in non-ADS holography. For example, if you do holography for Lipschitz space-times, there are certain deformations of anti-de Sitter space-times characterized by critical exponent. You found on the boundary that it induces a Newton-Cartan geometry, which is an example. It's seen in covariant formulations of post-Newtonian approximations in GR, covariant formulations of non-Lorentzian fluids. So non-Lorentzian fluids would be, for example, the non-relativistic Navier-Stokes, but now put on a curved background, and other condensed matter systems. Horava-Lipschitz gravity, also non-relativistic versions of various 3- and 2-dimensional theories, Chern-Simons and JT gravity. Appears in context of cosmology, black hole horizons, so-called ultra-local or Carroll limit of GR. There are actually interesting connections to double field theory. And then, if you then go to the realm of string theory, there are actually quite some interesting corners of string theory, and particularly there's a non-relativistic corner of string theory that I hope to tell you a little bit more about, and various related corners related to this non-relativistic string theory corner by U-duality. And finally, non-Lorentzian geometries appear when you do certain limits of vanilla ADS CFT, so ADS 5 CFT 4. Okay, that's a little bit of a primer, but so I hope after this talk you know a little bit more what I mean with these words, at least in some specific cases. I've now two also motivational slides. One motivation, and here I really use the word non-relativistic in this sense of speed of light to infinity, comes from considering this cube of physical theories that I'm sure you've seen many times, also called the Bronstein cube. where you have the three constants of nature: speed of light, Newton's gravity constant, and Planck's constant. And you know, why many of us are working on a daily basis, and also why we're here, is we want to understand this corner, quantum gravity, and for many people here in this room, string theory is a promising approach there. But whereas we very often think of, let's use the rules of quantum field theory and add gravity to it, or let's go start from classical GR and quantize it using what we know how to quantize field theories. There's sort of a third route that comes from this putative corner that I call NR, that we call NRQG, non-relativistic quantum gravity. So if you understand, say, this, that's one motivation. There's maybe like a third way to approach this corner. Now, once you're here, you might wonder, what is this and how does this fit with string theory and holography? And in particular, like roughly in this corner, holography is a duality between this corner, so string theory, and non-gravitational quantum field theories, like n=4, and this corner. So you could also suspect that if you understand this better, that there might be simpler or novel holographic dualities in this non-relativistic side of the cube. Interestingly enough, okay, it becomes a little bit of a regress. Even the corner of which this is the quantum theory of, namely NRG, sorry for all the abbreviations, but that's non-relativistic gravity, that has some surprising elements. If you would have asked me, because I actually drawn this corner in my GR class like 14 years ago, I always put Newtonian gravity here, inspire the students, but actually seen as a large speed of light limit or expansion of GR, this corner is actually more general than Newtonian gravity, because it includes it, but it also allows for strong gravitational fields, while still having non-relativistic tension space symmetries. But then, so this is sort of motivation one, very much related to sort of this non-relativistic side of the cube of physical theories. And if you actually zoom out a little bit more, there is actually a much larger landscape of non-relativistic theories. For one thing, if you could wonder here, there's the speed of light to infinity, so 1/c to 0 going to this corner. But what about sort of strong coupling limits, so the speed of light to 0 here, or h bar to infinity, etc. So, but in particular here, you sort of see another limiting case emerging from this cube, and that's this quite studied recently branch of theories called Carolian theories. We'll say more about that occur in the small speed of light limit. And again, you can consider the small speed of light limit of GR, but also of field theories, etc., etc. Then another point that I think is important to stress here is that beyond the small or large speed of light, there are actually more general limits in string theory. In particular because string theory is so rich, and we actually have many objects in string theory, not just particles, but brains. And that's sort of at the origin that you can do, there's a larger landscape of non-Lorentzian theories, and hence non-Lorentzian geometries that play a role in string theory. And typically they're actually related to the vanilla non-relativistic physics by dualities. And then another thing I like to, it's maybe kind of technical, but sometimes it causes some confusions. I'd just like to mention it here, and if I have time I mention a little bit more detail, is the concept of, if you play, say, with the parameter c, or 1/c, c is the speed of light, the difference between doing limits, like really a limit of a theory, and expansions. I'll say some more about that. Now, what's the common feature of this landscape of non-Lorentzian theories? That they're described on novel curved spacetimes that go beyond Riemannian or pseudo-Riemannian geometry. I call them here non-Lorentzian geometry in the most general sense. And these non-Lorentzian geometries, they then can appear, for example, in new type of gravity actions when you make them dynamical. These NL geometries appear also as backgrounds for relevant probes, and I will illustrate that. And then in addition, that's more like a string theory thing, if you have extended probes, so not particles, but strings and branes, then the physics gets even richer. And not only can the target space be non-Lorentzian, but the wall volume, which is now more than one-dimensional, can also show non-Lorentzian symmetries. I have to speed up a little bit because I was told it's only 25 minutes, but I just want to give a little bit of an example of what a non-Lorentzian geometry is. I will do that by telling you what Newton-Cartan and Curonian geometry are, and then flash some applications. So some of these transparencies I can actually do very quick because they're very simple, but I try to kind of keep it general. We have, of course, all learned in GR that the geometry of space and time is intimately related to the local symmetries of space and time. And this really comes to a very beautiful manifestation in GR, where, following Einstein's special theory of relativity, we insist on that the local symmetries of space and time are Lorentz or Poincaré. And that's, of course, what gives you a Riemannian geometry. But this link holds, obviously, much more general. So, in a nutshell, what non-Lorentzian geometries are just replace the local symmetries of space and time by some other symmetry group. That's what I call here space-time symmetries. Let's say the bare-bone space-time symmetries that we would like to include. Of course, you could also deviate from that, but are like having time translations and space translations and spatial rotations for isotropic systems. But then, one of the distinctions, and there can be more distinctions if you're in string theory because it's a richer theory, but a first-order distinction of space-time symmetries is obviously what type of boost you have. So what type of relations between space and time do you have? Lorentz, okay, we all know, non-relativistic. We actually, of course, know maybe even better. That's the large speed of light limit. And then the Carroll is the small speed of light limit of a Lorentz boost. It looks like this. So Carroll symmetry, whereas in Galilean space-time, time is absolute. In Carroll geometry, space is absolute. And I will now quickly show you what the geometries are that make these symmetries local. They are known as Newton-Cartan and Carroll geometry. I just say on the side, and some people find it a little bit anachronistic and blasphemic to throw Aristotle in the game. But, and this is actually a term coined by Penrose, but you could also say, I'm interested in the geometry or the symmetry where there are no boosts at all. And that's called the Aristotelian, and actually has had quite some interesting applications. For example, in non-boost invariant hydrodynamics and in fractal physics. Are there questions at this point? I know there's a 10-minute question session, but maybe there are some burning questions. And this is what happens with the light cones, of course, in these limits. 45 degrees flattens out or closes up, and that's why this light cone really closing up. That's why Carroll geometry is also called the ultra-local limit, because things really can only move, in the ultimate limit can only move in time and not in space. So, we'll do this very quick. So, what pseudo-Riemannian geometry is to Poincaré is essentially Newton-Cartan geometry to the Galilean, or more precisely, the Barkman symmetry. I give the Barkman algebra in a second. This, I think, is a very beautiful insight of Cartan, like 1923. So, just some years after Einstein's theory, that he realized, the fact that Einstein geometrized gravity, that's a consequence of, insisting on diffeomorphism invariance. That's not a unique property of GR. you just have to change the tangent space symmetries to Galilean, or rather Barkman symmetry. And he managed to geometrize the Poisson equation of Newtonian physics using that geometry. Now, what's one, by the way, I have very few technical slides, this may be the most technical, but what's one way to think about Newton-Cartan geometry? Actually, in a very nice paper by Andringa, with the Groningen group of 2012, is by thinking of, indeed, this local symmetry that you want to have. It's not Galilean, but it's Barkman. Galilean symmetry, of course, we know that you have this commutator, H with boost gives translations. Now, in Galilean symmetry, these would commute, but Galilean theories typically have a mass, and mass is not energy anymore, so you need an extra generator that encodes mass. That's this central element appearing in this commutator. So the algebra together with the mass generator is called the Barkman algebra. And you can, it actually follows from an Enono-Wigner contraction, not of Poincaré, but of Poincaré times an extra U1. Okay, then you can make this local by gauging it, the symmetry and introducing the Barkman valued gauge field. And then you can show, and it's sort of a trick to, people, half the room might have seen this, how you do this for Riemann in geometry. You change the local translations for diffeomorphism invariance with some trickery. But at the end of the game, you can show that the gauge transformations corresponding to these symmetries here can reproduce the transformations on the local Galilean boosts and rotations and diffeomorphisms. And the metric fields then are the independent fields here. So these connections are dependent, and the independent fields are a time-like Vielbein, a space-like Vielbein, and a U1 gauge field that's dual to this mass generator. And out of this you can make a rotational invariant metric, spatial metric. So, Newton-Cartan geometry, instead of a G mu nu, instead of a metric, you have the objects tau, h, and m, or tau, e, and m. That's what Newton-Cartan geometry is, and then, of course, you have to say how the things transform. This is how they transform on the local Galilean boost. They are tensors under diffeomorphisms, but they transform in a certain way on the local Galilean boost. And you can write down the sort of analog of a Christoffel connection. I'm not giving it because it's a little technical, but so you have a Christoffel connection expressed in terms of tau, h, and m, just like you have a Christoffel connection expressed in terms of g. And here's sort of a picture. So there's a time-like Vielbein, there's a spatial metric. Time is orthogonal to space, so h is rank d minus 1 in d dimensions. And there's a gauge field living at every point. And now, if you study more carefully the connection, you actually find that your connection now has an intrinsic torsion that's proportional to the d of tau. Newton-Cartan considered the torsion-less case, that corresponds to absolute time, but it was not really appreciated, and it came out of sort of holography that you should relax this and allow for torsion. In particular, twistless torsion is sort of the most interesting case. The tau is not zero, but still you have this hypersurface orthogonal condition. Okay, here's then, okay, can give many actions, but here's a very simple action. You can wonder, how does a non-relativistic particle couple to that geometry? Well, there are two techniques to find it. Do a null reduction of a relativistic particle, or do the large speed of light limit of an extremal charged particle. And here you see how the walled line of a particle, x, couples to h, m, and tau. And that shows a covariant kinetic term and a covariant potential term. Just to say, well, you could say, why is this particle even interesting for this audience? But I was told that Jan briefly mentioned the BFSS limit of a non-perturbative description of M theory in terms of d0 particles yesterday. In fact, the d0 particle is an extremely charged particle in string theory. And the matrix string theory on a curved background space-time can actually precisely be obtained from this limit applied to the dBi action of a D0 brane. And in that sense, thanks, D0 branes couple to Newton-Cartan geometry. Just to make the geometry even maybe more intrinsically clear, precisely if you have a more general field theory with Galilean symmetries and you want to couple it to a background field, the background field that you can and want to couple to it is torsional Newton-Cartan. And you precisely have the response to tau being the energy current, to h the spatial stress, and to m the mass current. It's kind of surprising, I think, and of course Son pioneered this from the condensed matter side to describe the fractional quantum Hall effect. It's kind of surprising, I think, from a condensed matter point of view, that these sort of geometric techniques have not been used before. In particular, it's a very nice organizing principle for effective theories and hydrodynamics. What about Carroll geometry? And you might see heard a little bit about it also in different contexts. It's sort of the dual object. I'll just say, essentially you can get it again in the same method I showed you before by gauging the Carroll algebra. Carroll algebra has a different type of commutator structure, namely now translations and Carroll boost commute to the Hamiltonian. And so that's how you then get Carroll geometry. And okay, in view of the time, just leave this. Just say in 1 second that sort of Carroll symmetry has appeared in many contexts, sort of modern contexts, both in terms of gravity, flat space holography, cosmology, and black hole physics. So it's sort of a very nice universal limit, even though it looks a little weird, right, to send the speed of light to 0. I emphasize that limits versus expansions, you have to be a little bit different. In view of the time, let me leave it with that, but then you can ask me what the difference is. Essentially, it has to do whether you want to really insist on canceling divergent terms in the large speed of light limit or some other scaling limit, or whether you like just to get an action expanded. Both have their merits, and they are, of course, well, one is contained in the other, but yeah, it's a little subtle. Again, in view of the time, let me just say that I showed you sort of an intrinsic definition of Newton-Cartan and Carroll geometry, but you can also get it from a large speed or small speed of light expansion of GR, and that has been done very carefully in the last years, shows you it's actually a very nice way to get the corresponding dynamical actions on these novel geometries, because you might wonder what's the analog of the Einstein-Hilbert action. So you can take the Einstein-Hilbert action, put in a metric, and you sort of, well, you get ready to do the expansion by splitting time and space. This is still totally Lorentz symmetric, but now you assume that these are power series of c squared or 1 over c, and you start expanding. And you can sort of imagine that you can do this maybe from the Einstein-Hilbert action and get now gravity actions on these novel type of geometries. And they actually have very nice and interesting properties. Now, in the last part, then, let me say something about string theory. So far I actually talked about particles and some relatively simple symmetries, but Gomis and Oguri found way back in the 20th a very interesting corner of string theory as we know it. You can do it both for the bosonic case as well as the supersymmetric case. And they found an action using a limit that's very similar to what I described, how you get the non-relativistic particle. Namely, you take a near critical limit using the fact. So you now switch on a near critical B field for a string, using the fact that the string is an extremely charged object, not particle, string. And this is sort of an interesting self-consistent UV complete corner of string theory with the Galilean invariant dispersion relation. Here's the action in conformal gauge on a flat background. And it's actually only recently, well, so in the last 5 or 7 years, that motivated by these advances of understanding non-Lorentzian geometries, that the question was asked, what is the general target space that such non-relativistic strings move on? And there are actually various techniques, but I think the simplest phrase, you can just think about how you did it for the particle. You can either do a null reduction of a relativistic string. Essentially, it has some elements of doing a light-like T-duality along a null isometry. Or you can actually stay in the same dimension, so you not do a reduction, but do a large speed of light limit. And what you find is the correct geometry that now strings, non-relativistic strings, move in. It's some avatar of the Newton-Cartan that I showed you. There's also an underlying algebra that you can gauge. I will show it. But it's known as torsional string Newton-Cartan geometry. It actually has a Riemannian geometry in the transverse space that's fibered over a two-dimensional Lorentzian base, and then there are stringy boosts relating the base to the transverse space. Okay, and I just flash here the action. The geometry looks like this. It now has a Wald volume field line in the 0 and 1 direction on the Wald volume. There's a 2-form potential instead of a 1-form, and this is the action. Okay, I finish in 45 seconds. Just to, I think, well, it's very nice that Jan Rossel will give a talk after this. You can wonder about beta functions and non-relativistic, what kind of non-relativistic supergravities they give. I think Jan will say something about that. There has been a very rich study. And then you can wonder, once you have the non-relativistic string corner and have a nice geometric description of this, and you think of it in the context of superstring theory, where we have various interesting perturbative and non-perturbative dualities, you can wonder what kind of other corners can I reach. And here's sort of an overwhelming web, but it's more like to give you the idea that this non-relativistic string theory that I quickly discussed is actually related by dualities to many other corners that have been studied before, like BFSS matrix theory or non-relativistic M theory. But the overarching novelty here is that we now know the target spacetimes on which these different decoupling corners of string theory live. And there are non-Lorentzian target space times. Okay, so then, I could make a longer list, but just to say, on sort of the pure gravity side, because you don't have to be necessarily interested in string theory to look at these things, but on the pure gravity side, there are actually quite some interesting things still to do with this geometric approach and understand post-Newtonian approximations, applications to non-relativistic quantum gravity, explore Carroll's side more, the string theory side that I said, various generalizations. And then, so I hope to have made clear that there is some kind of general lesson that non-Lorentzian geometries, even though they sound maybe a little esoteric, that actually are quite a natural tool for study of corners of known relativistic theories. Thanks.
Any questions? Yes.
Can you start with a non-relativistic string and get from it an effective non-relativistic dBi for gauge fields?
Yeah.
And for instance, see what is the deviation of Maxwell theory and try to do some experiment to exclude it or stuff like that?
Interesting questions, and various of my colleagues there are various interesting papers that have done this by looking at the open string sector of non-relativistic strings, and you find indeed some kind of non-relativistic dBi that actually in the alpha prime to 0 limit becomes a theory that actually was already studied, well not covariantly but in flat space decades ago, which is Galilean electrodynamics. So to say it another way, Galilean electrodynamics actually has a dBi generalization that follows from the open string sector dBi boundary conditions.
You had two pictures of bread somewhere.
Thanks for asking.
I wasn't
Okay,
entirely
they're not
sure
there.
what was.
Thanks for asking. So one picture was your classic bread with the slices, and the other was and very nice you asked it here, was the Italian ciabatta. That's called the first bread with the slices, Dutch bread, and the Italian ciabatta, the Italian bread. So this was to signify that the Dutch bread is flat due to Catan space, but you have very nice slices of equal time lined up. What Jurte Catan does is to make it into an Italian bread where the space is curved. Thanks for the question.
Okay, that was not entirely obvious from.
No, I've always put this picture to advance questions. It has worked for me.
Another question that I had: if you take the non-relativistic limit of ADS-CFT on both sides, do you get a non-relativistic holographic duality?
Yes, it's just, and there have been, there are different sort of approaches to this. I had to skip a slide, but so one approach that we have been pursuing is, because those depends a little bit how you do the limit, but so one limit that I'm more familiar with, we see pieces of the puzzle, so if you do a so-called near BPS, or scaling limit on the n=4 side, then you can implement that on the gauge, on the string theory side, and see that you actually get some, you actually see it's implemented by a double limit on the string theory, both the limit in the target spacetime and the Walsh. Okay, so there's sort of a proposal of emergent non-relativistic theory from so-called spin matrix theory. There have been some recent papers by Andrea Fontanella and Nieto that do what you say just more directly, just take any ADS-CFT, as we know what to do CFT. Yeah, I've not studied the papers in detail because there's some twists and turns that I cannot fully follow there. But it seems a logical route. But one surprising thing, what I found surprising, if I understood it well in that paper, is that they actually get, that on the gauge theory side, this becomes some kind of Galilean electrodynamics with a U1 to the n symmetry, not with a non-abelian symmetry, but with a U1 to the n.
You should use the microphone.
Sorry. So I found very. So the gauge theory is just n factors of a U1 Galilean electrodynamics type of limit that you would get just from taking a standard non-relativistic limit of n=4. So it's a very good question, and I think the last word is not being said, but I would hope that in some years there's a clear answer to that, because I would expect there's a really clear duality where you can actually compute things on both sides.
Thank you. Okay, I'll take 2 more questions.
About Carolian limit, I mean, what insight does the Carolian limit give you on a relativistic system? Namely, why should we consider this limit?
Okay, a nice question. Okay, I think the easiest answer is GR is a very complicated nonlinear theory. Any kind of tool that gives us maybe a handle to explore solutions can be useful. Now, and the interesting thing is, and you could also say that's trivial, but because the theory becomes ultra-local, Einstein equations actually reduce to ODEs. Actually, so the leading order action that you get from Einstein-Hilbert is roughly S extrinsic curvature squared. But that's actually quite nice because you can find quite some interesting non-trivial solutions. From, yeah, besides because it's all.
It's actually similar to the cosmological similarity.
Thanks for putting that up, because actually Mark Hanot, in a very visionary paper called the zero signature limit of GR, because if you think about it, it's the same as the zero signature limit, right? Because C squared is in terms of in front of DT squared. He explored this in the 80s while he was at Princeton, and then also in later papers. You can show that a subset of solutions is related to the geometry that you see if you're very close to the singularity of the black hole.
Space flight.
Sorry?
The space flight.
Space flight singularity, just thanks. So that's just one, but I can tell you more interesting applications.
One more question.
You mentioned T-duality in a null direction, so I wanted to ask what that means, because if you use the usual Boucher approach, you find that it doesn't work for a null direction because you have 1 over the norm of the killing vector, which would be 0 for a null vector.
Yeah, so one way to, there's this Seiberg-Sen prescription to see it as a limit, as an infinite boost limit of a space-like T-duality. Well, I can show you the details. There is a way to make sense of it, even using, in fact, the Rorschach for Linde gauging prescription. You just have to take an appropriate scaling limit. I can maybe put it another way. Think about, I don't know if this helps, but actually, non-relativistic string theory, if you do a T-duality, okay, first of all, there are many details I couldn't say. Non-relativistic string theory always needs a compact direction in the longitudinal direction because you need to have non-zero winding. You can see that to make sense of the physical spectrum. You can actually show that if you do a regular T-duality along this longitudinal direction of the non-relativistic string, you end up with the DLCQ of type 2 string theory. So one way actually to say is that at the expense of non-relativistic target space symmetries, you can get a reformulation of something you don't maybe have doubts about, namely doing the DLCQ. But it's a dual perspective.
Okay, let's thank Niels again for his nice talk. So the next speaker is Jan Rossil, who's going to present non-Lorentzian supergravity.
Okay. Well, first of all, let me thank the organizers for giving me the opportunity to talk here. So I will follow up on the talk by Niels, and I will basically supersymmetrize part of what Niels said. So I will talk about non-Lorentzian supergravity. And in order to motivate why this is an interesting thing to do, let me just start by flashing a partial list of some of the things that Niels mentioned, some of the applications of non-Lorentzian geometry that Niels mentioned. So Niels basically said that non-Lorentzian geometry is a really useful tool if you want to describe systems that take place in some kind of non- or ultra-relativistic regimes. It has been applied to like holography, construction of effective field theories in strongly coupled condensed matter systems, non-relativistic fluids, large and small C expansions of general relativity. Recently also in the context of celestial holography and the connection with Caroline physics. And the one thing that I would like to highlight, because it will be one of the motivations for this kind of work, is this non-relativistic string theory here that Niels mentioned, this kind of limits of relativistic string theory that was invented by Gomes and Oguri and also by Danielson, Goyosi and Kruczynski in the early 2000s. As Niels mentioned, it's essentially kind of a subtle extremal limit. It's in fact an infinite tension limit of relativistic string theory where you assume that your string is compactified. And it's characterized by non-relativistic dispersion relations. So the spectrum of string excitations has non-relativistic dispersion relations, and they interact via some kind of Newtonian gravitational interactions. Now, when I mention the word string theory, then it's of course very obvious to think that you should add super to it. You should consider superstring theory. So you can also consider non-relativistic superstrings. And then, of course, there are natural questions that pop up. For instance, what is the analog of supergravity in these non-Lorentzian superstring theories, in these non-relativistic superstring theories? So these non-relativistic superstring theories exist. Thus, there exists something like non-relativistic supergravity that plays a similar role as relativistic supergravity plays for relativistic string theory. There are other reasons why you might be interested in non-Lorentzian supergravity or non-Lorentzian supersymmetric curved spacetimes. For instance, you might want to use non-Lorentzian supergravity to construct supersymmetric field theories on curved non-Lorentzian backgrounds. You might be able to try to see whether you can localization techniques to, for instance, compute certain observables in an exact manner in such theories. Recently, there's also been some interest in supersymmetric condensed matter field theories. In particular, there was a paper quite recently by Gromov et al., where they consider some effective theory for some, well, essentially some effective theory in some gapless fractional quantum Hall state. And they, well, basically conjecture that it should be described by some supergravity theory. And it's not your standard supergravity theory. It is really some kind of non-relativistic supergravity theory. Now, as soon as you start thinking about the details of what it would mean to merge supersymmetry with non-Lorentzian geometry, or to what it would mean to construct non-Lorentzian supergravity, then you quickly find that it's quite subtle, it's quite non-trivial, and there's also quite interesting puzzles that appear. There's a couple of things that work quite differently from standard ordinary supergravity. The good news is that in recent years we've developed a lot of technology concerning non-Lorentzian geometry. Many of these questions have now become accessible. So what I will do in this talk is kind of give you an overview, a short overview of what has been done on non-Lorentzian supergravity. And so from the start, I can say that the only examples that have been considered so far are cases in which the underlying geometry is what I call p-brane Newton-Cartan geometry. That includes the Newton-Cartan geometry that Niels discussed, and it also includes the stringy Newton-Cartan geometry. It's in fact a generalization to generic p-branes. I will explain what this p-brane Newton-Cartan geometry is in a bit more detail. I will focus on the aspects of it that are important for supergravity. Then I will briefly say something about the methods that we used so far to construct non-Lorentzian supergravity theories, and then I will give two examples that are both related to non-relativistic string theory. The first example is a minimal supergravity theory in 10 dimensions that is relevant for non-relativistic string theory. And the second example that we are currently trying to work out deals with a non-relativistic version of 11-dimensional supergravity. And then I will end with some outlook and basically a huge list of things to do and things to consider. Okay, let me start by giving a bit more details about these p-brane Newton-Cartan theories. So these p-brane Newton-Cartan theories, well, they are essentially the spacetimes that non-relativistic particles, strings, and branes move in. And you should see them as a limit of Lorentzian geometry, but it's not the standard C to infinity limit, but you effectively take the speed of light only to infinity in directions transverse to the p-brane. Basically, if you think about the local light cone, you should really think of the C to infinity limit as a limit in which you send C to infinity only in the transverse directions. So part of a local light cone flattens out, but it's only in the transverse directions that the light cone opens up. Along the world volume directions, along longitudinal directions to a p-brane, spacetime still is entirely Minkowskian and the speed of light stays finite. Now, to describe the geometry in more detail, since I do supergravity, I will need a Vielbein formulation, so I can essentially describe the Vielbein formulation of p-brane Newton-Cartan geometry in analogy to how you do it in Lorentzian geometry. Unfortunately, I see that the indices got a bit messed up by the projection. So in standard Lorentzian geometry, you have an invertible Vielbein that transforms under local Lorentz rotations in the fundamental representation. And the first thing that you should do is give the analog of local Lorentz transformations for these p-brane Newton-Cartan geometries. And the way in which you do it is you take the d-dimensional index A hat, the d-dimensional Lorentz index A hat, and you split it in two subsets. One that I denote by capital A, that takes p+1 values, and then the one that I call small a, that takes the remaining d minus p minus 1 values. The capital A I will call longitudinal, and the small a I will call transversal. Once you've done the splitting of the indices, you can replace the local Lorentz transformations by a group that's, unfortunately the projection is really messing my slides up quite badly. So it's essentially a semi-direct product of boosts with a direct product of SO1, P and SOD minus P minus 1. So the SO1, P factor that's, is basically that mixes the longitudinal directions, so that's just an SO1, P Lorentz group that mixes the longitudinal directions. Then you have transversal rotations that mix the transversal directions, and then the boosts, they send transversal directions to longitudinal ones, but not vice versa. You can then introduce the Vielbein structure. To do it, you introduce two Vielbein, one that I call a longitudinal Vielbein and one that I call transversal. And they transform under the structure group that I've just shown in the fundamental representation, essentially. So tau only mixes to itself according to longitudinal Lorentz transformations. The E transforms into itself under transversal rotations. And moreover, it shifts to the tau under boosts. Once you have these Vielbeine, you can introduce dual frame fields as well, just in the standard way. And then using these Vielbeine by squaring them appropriately, you can introduce two metrics that are degenerate, one of rank p plus 1, that is a longitudinal Lorentzian metric, and then one co-metric of rank d minus p minus 1 that is just a standard Euclidean metric. As Niels also mentioned, you need an extra ingredient. It turns out that you also need to introduce a p plus 1 form that transforms under boosts to the E's and the taus. That's an object that will couple to non-relativistic p-branes. So in the p equals 0 case, for instance, this is the central charge gauge field mu that Niels showed. In the p equals 1 case, that's a stringy case, then it's really the b mu field that Niels, or the m mu field that Niels showed. What this field does is it does actually something very physical. It takes care of conservation of brane tension. That's something that you want to impose separately in non-relativistic theories. So for instance, in the case of p equals 0, this the case of a non-relativistic particle, there is just an ordinary gauge field that couples to the neutral current that is associated to the symmetry that implements conservation of mass. And conservation of mass is really something that you want to implement separately in non-relativistic theories. So the picture that you should have in mind, that I can draw easily, that's for p equals 0 and p equals 1, is that locally these geometries look something like this. So for instance, for the p equals 0 case, you have space-time that's locally you can slice up in spatial slices, and then there's a time direction, and moreover there's an extra mu field to which massive particles couple. And similarly for the p equals 1 case, that's a stringy case. Locally, there's a notion of transverse space to the string, and then there are some kind of world volume directions that are singled out, and there's an extra two-form field that couples to a string according in the standard way with a Besom-Minot term. That gives you the metric structure of the geometry. You should then also, of course, give the connection structure. You can introduce spin connections in the Vielbein formulation, in analogy to how you do it in Lorentzian geometry. So in Lorentzian geometry, you introduce a spin connection that satisfies the first Cartan structure equations. In p-brane Newton-Cartan geometry, you will introduce 3 spin connections that are associated to each of these factors of the structure group, and you will just write p-brane first Cartan structure equations that are really very analogous to the standard first Cartan structure equations in Lorentzian geometry. So you just take like properly covariantized curls of the Vielbeine, and since the B fields, the p plus 1 form fields also transforms under boost, you can also use it to introduce a first Cartan structure equation. There are 2 qualitative differences with standard Lorentzian geometry that are kind of related. One difference is that these first Cartan structure equations do not determine the spin connections uniquely in terms of the Vielbein and torsion tensor components, at least not for p bigger or equal than 1. So these p-brane first Cartan structure equations, they don't single out a unique metric compatible connection, but a whole family of metric compatible connections. And then more important for my talk is the second related difference. That is that if you look carefully at these first Cartan structure equations, then you see that some of them do not contain spin connection components. In particular, you can take, for instance, suitable projections of the first Cartan structure, the first Cartan structure equation along transversal and longitudinal directions, and you will see that for some of these projections, the spin connection omega mu AB drops out. That is expressed mathematically by saying that p-brane Newton-Cartan geometry has intrinsic torsion. And this intrinsic torsion, these are just the torsion tensor components that appear in these first Cartan structure equations that do not contain spin connections. Why is that important? Well, it leads to a very qualitative difference with standard Lorentzian geometry. In standard Lorentzian geometry, you know, if you impose constraints on the torsion, then it just means that you choose a particular connection. Here, if you impose constraints on these intrinsic torsion tensor components, then it amounts to choosing particular connections, but something more as well. Namely, it amounts to imposing geometric constraints. So you see that if you put some of these intrinsic torsion tensor components equal to 0, then you really get constraints on the curl of this longitudinal Vielbein, and these are really kind of constraints, differential constraints on the metric structure. That's very different from standard Lorentzian geometry. You can classify all these constraints for generic p-brane Newton-Cartan geometries. You can give a geometric interpretation. I'll just single out two of them. The first one is essentially saying that this one here is entirely equal to 0. That is the p-brane analog of this twistless torsional constraints that Niels showed. So that basically means that your manifold can be foliated in d minus p minus 1 dimensional transversal leaves. If you put all intrinsic torsion tensor components equal to 0, it turns out that there's a notion of absolute world volume. In the p equal to 0 case, that just translates to saying that there's a notion of absolute time. That's the standard Newtonian absolute time notion. So in this geometric framework, this is implemented by imposing intrinsic torsion constraints. Okay. So that's what I need concerning the geometry, and now I can start discussing more about supergravity. So the central question that we basically want to ask ourselves is always like, is non-Lorentzian geometry compatible with supersymmetry? Can you construct something that can be called non-Lorentzian supergravity, and what is its structure? So as I said, so far this has mostly been done for the cases in which the underlying geometry is one of these p-brane Newton-Cartan geometries. And there are essentially two types of methods that you can use to construct non-Lorentzian supergravities. I call them intrinsic and extrinsic. By intrinsic, I just mean direct construction starting from something non-relativistic. You know some non-relativistic superalgebra, you know representations and so on, then you can try to use that to directly construct non-Lorentzian supergravity theories. That method has a drawback, namely that there's not so much known in general about non-Lorentzian superalgebras and their representations, so there's still quite a lot of work that needs to be done there. Nevertheless, it has been applied in the simpler setting of 3 space-time dimensions for p equals 0, so for like these particle Newton-Cartan geometries. Essentially, what has been done there is that people have come up with a whole zoo of non-relativistic superalgebras that you can gauge to construct non-relativistic supergravity theories in 3 dimensions. The second method that I will illustrate in a minute in this talk, that I call extrinsic because it refers to some kind of relativistic counterparts. And it's essentially starting from some relativistic supergravity theory and then using that to construct something non-relativistic or something non-Lorentzian, either by doing a null reduction, as Niels mentioned, or by taking limits, non- or ultra-relativistic limits. That has been used so far in d equals 10. And currently we're also using it in d equals 11, and that's what I will explain next. The drawback of that is that it can be rather subtle, and part of the aim of the next section is to show some of these subtleties that appear. It's also not really sure whether this really exhausts all possibilities, so it might be possible that there exists non-relativistic or ultra-relativistic supergravity theories that you cannot obtain easily from a limit. That is entirely possible. Let me illustrate this limit procedure in the case of minimal supergravity in 10 dimensions. So there the starting point is n equals 1,0 supergravity in 10 dimensions. With field contents, the Vielbein, the Calpramont 2 form, a dilaton, and then a gravitino and a dilatino that are left and right-handed Majorana-Weil spinors, respectively. And then what you do to take the non-relativistic limits is, well, you start again by doing the splitting of the flat index A hat in two longitudinal values that I will denote either by 0 or 1 or in light cone notation by plus and minus, and then transversal directions. And then what you do in order to take the limit is first you propose an invertible field redefinition and also a redefinition of all the parameters, Lorentz transformation parameters, supersymmetry parameters, etc. And this field redefinition goes with a parameter that you introduce that I call C, that is morally speaking the speed of light. It's really just a formal expansion parameter at this point. So what you do is you rescale the longitudinal components of the Vielbein C, while the transversal components you leave untouched. For the fermions, you split them up in two representations, in two separate representations under the transversal rotations. I call them plus and minus, and these you rescale differently with factors of C. And then the funny one, that's the expansion ansatz you take for the B fields. So you say that the B field has a C to the 0 term that is just another 2 form small b. And then there's a C squared term that is essentially a wedge product of the two taus. That is actually motivated by non-relativistic string theory because this is the ansatz that you take in order to obtain the non-relativistic string action, the curve space analog of the Gomes-Okori non-relativistic string action from the Nambu-Goto or Polyakov relativistic string action. So this is basically what motivates us to take this ansatz for B. What you then do in order to take the limit is essentially you plug in this ansatz in every quantity that you want to consider. Action, transformation rules, equations of motion. You expand in powers of 1 over c squared, and the limit consists of taking the leading order term in such an expansion, ideally. So if you do it, for instance, for the bosonic transformation rules, then you see that generically you get a term at order c to the 0, and then a term at order c to the minus 2. So the limit just consists of dropping the c to the minus 2 terms. And you see that for the tau, the E, and the B fields, you essentially regain these structure group transformations that define what Newton-Cartan geometry is. So these transformation rules under longitudinal Lorentz transformations, transversal rotations, and Galilean boosts. For the fermions, you find that under boosts, one goes to the other, but not vice versa. That's classic non-relativistic behavior. And one thing that is also very peculiar is that there's an extra symmetry that appears that you only see when you really study the equations of motion and the action, and that's the dilatation symmetry. That does not really come from a limit of relativistic transformation rules, but it's just a fact of life that after you've taken the limits, then it turns out that the theory exhibits an extra emergent dilatation symmetry. You can expand the action as well. Generically, generically, you expect that there would be a term at order c squared because some of the terms in the action start at order c squared. However, it turns out, and this is really due to this B field redefinition, that there are some cancellations that happen that ensure that this term at order c squared vanishes exactly. So the expansion of the action starts at order S0, starts at order c to the 0, and you would then say that the limit of the action is given by this S0. It's by default invariant under these zeroth order bosonic transformation rules. So far, so good. However, when you look at the supersymmetry transformation rules, then it becomes a bit more subtle because the expansion of the supersymmetry transformation rules starts at order c squared. Then it has a term at order c to the 0 and a term at order c to the minus 2. So naively, you would say that the limit is given by the leading order term. So naively, you would identify the non-relativistic supersymmetries with this c squared term. But that cannot be true. If you look carefully at the exact expressions, you see that they can never give rise to non-relativistic supersymmetry. In fact, if you look at the terms that order C2 to 0, then you see that these are really the transformation rules that you want that can constitute non-relativistic supersymmetry. So there is this divergent part in the supersymmetry transformation rules that you have to deal with. And you can actually deal with it by imposing intrinsic torsion constraints. And this is something that is very typical in constructing supergravity theories. It also happened in these three-dimensional examples that we constructed using intrinsic methods. You always have to impose some sort of torsion constraints. And here you see it happening also. You see it arising from the limits because you have supersymmetry transformation rules that diverge. So in this case, it's actually quite nice. It turns out that you have to more or less constrain half of the intrinsic torsion to be equal to 0. And the nice thing is that this is a supersymmetric thing to do. These constraints are invariant under the zeroth order supersymmetry transformation rules. So usually when you impose constraints, you have to do it in such a way that it's compatible with supersymmetry. So you have to vary the constraints and then impose the variation of the constraints again as constraints, and then you have to vary that again, and again you might get new constraints. You might get a whole tower of constraints that you need to impose in order to have compatibility with supersymmetry. Here it turns out that it's very easy, you just have to impose these constraints and you're done. So I mentioned this dilatation symmetry. You also get some kind of supersymmetric analog of that. It turns out that there are emergent fermionic shift symmetries. There's some kind of a superconformal symmetry appearing. They are really ordinary shift symmetries. They take the form of like Stuckelberg symmetries. So that kind of means that with respect to the original relativistic starting multiplets, there's some kind of multiplet shortening going on here. There are some components of the multiplets that you can get rid of in a trivial manner just by gauge fixing these fermionic shift symmetries. If you examine the equations of motion, you can also take the limits of the equation of motion. That's a bit subtle, but it can be done. And if you examine them carefully, then you see that it's basically, it gives you a diffeomorphism covariant version of the Laplace equation, where the role of the Newton potential is played by the longitudinal components of the two form, the Kalb-Ramond two form. So that plays the role of the non-relativistic Newton potential. And the bosonic part of these equations of motion also exactly corresponds to the beta functions of non-relativistic string theory. Those have been calculated by Gomis, O, and Jan and Yu. And we can basically reproduce this by this limit procedure from the, well, in SNS gravity equations, or in this case, the supergravity equations of motion. To finish, let me briefly say something about the 11-dimensional case. You can deal with it in very much the same manner. So again, you can take the limit in a very similar way. You can propose these kind of field definitions that involve parameter C. In this case, you have a 3 form, but it's a very analogous ansatz that you take as the one for the 2 form that I've shown. In this case, not all the divergences in the action are cancelled by this ansatz. It turns out that there are some remaining divergences, but you can regulate them, you can take care of them because they take the form of a perfect square, and then essentially you can use a Hubbard-Stratonovich transformation to turn a C-cube term, a divergent C-cube term in the action, into a C to the 0 and a C to the minus 3 term. So in this way you can regulate this limit procedure. One difference with the 10-dimensional case is that, again, you get emergent shift symmetries, and again, you get divergences in the supersymmetry transformation rules that you can deal with by imposing constraints. But here, in this case, life is not so nice as in 10 dimensions. These constraints are not supersymmetric. So again, you have to impose intrinsic torsion constraints. In this case, you in fact have to impose that most of the intrinsic torsion is equal to 0. These constraints are not supersymmetric, so you have to vary them and impose their variation as a constraint. You get new constraints whose variation you have to impose as a constraint, etc., etc. So you get a whole tower of extra constraints that constrain some of the curvatures of the manifold. But it can be done. One thing that I want to mention also is that this theory actually has a non-trivial supersymmetric solution that has been proposed recently by Lambert and Smith. So what Lambert and Smith did was they considered a particular scaling limit of ABGM theory that is non-trivial in the sense that it describes motion on the moduli space of the Hitchin equations. And so They conjectured that there should exist a limit of the standard relativistic M2 brane solution, particular scaling limit of the standard M2 brane solution, that is fully supersymmetric, or at least whose near horizon limit is fully supersymmetric, and that we indeed reproduce. So we can check that this solution is indeed a solution of our equations of motion, and that it's fully supersymmetric. Okay, so let me finish. Well, I've basically tried to argue that non-Lorentzian geometry and supersymmetry can be made compatible. It's slightly non-trivial. There are interesting structures that appear that need to be explored. There's a whole list of things to do, both from a technical point of view. So far, we've done this on a case-by-case basis, just constructing examples in 3 dimensions because it was easy. We could do the cheap thing, so to say. In 10 dimensions, we managed to figure out how the limit works. But it's fair to say that what we've done so far is not very systematic, and we really need analogs of standard techniques like superconformal tensor calculus, realomic approach, superspace techniques to do. We need to adapt them to also construct non-Lorentzian supergravities. One can also start looking at other types of non-Lorentzian supergravity. One thing that is very interesting that it would be to look at solutions. So I mentioned these Lambert-Smith solutions. It would be very interesting to look at, to really explore the solution space of these non-Lorentzian supergravity theories and kind of try to see whether they can act as duals of various decoupling or scaling limits of supersymmetric field theories that one can consider. Another interesting thing to do would be to use this formalism to construct supersymmetric field theories on curved non-Lorentzian backgrounds and to see whether some of these theories can be amenable to localization techniques. And as a take-home message, well, I can just say that experience has taught us that relativistic supergravity always seems to know more than meets the eye at first sight. So it really contains the seeds of many important lessons that we've learned for quantum gravity and non-perturbative QFT. And in recent years, we've really developed tools and technology that allow us to check whether non-Lorentzian supergravity might hold similar lessons for their non- and ultrarelativistic counterparts.
Questions?
Thanks. That was just a question about the solutions, because you mentioned that to have supersymmetry, you need certain torsion constraints.
Yeah.
So have you checked, or can you see in some, let's say, solitonic solutions of relativistic supergravity or string theory that after the limit automatically, after the non-relativistic limit, automatically those solutions satisfy those constraints?
Yeah, we haven't done it in full detail. So the only solutions that we checked so far are this Lambert-Smith solution, and then of course the standard M2 brane solution. They satisfy these torsion constraints, but yeah, I cannot make any general statement at this point.
But would you expect that there's sort of a one-to-one correspondence, or
yeah,
new? Well, do you have any expectations?
I would expect if you manage to take the limit in the correct way, but that's sometimes a bit subtle for solutions. I would expect that it works, but at the moment I cannot make a very general statement. I have to say.
You want to make a comment? Just a comment, and then I...
It wouldn't be inconsistent if it doesn't work, no? It just means that that solution after the limit is not supersymmetric.
Yes, yeah, that's true, yes.
Did anyone try to approach these supergravities, non-relativistic supergravities, from superspace side?
No, not so far. Not. No, that would be very interesting to do. It's really so. I have to say, this tower of constraints that we get, that really it really cries out for supersymmetry. You get a whole multiplet of constraints, and this is really something that cries out for superspace. So it will be really useful and handy to have a superspace formulation. So far, we have not done it.
Yeah, thanks.
There was a question.
In the Outlook, there is some point about dualities. So I was wondering, have people studied toroidal compactifications in those supergravities, and is there some equivalent of T or U dualities?
Yeah, that's a slightly subtle. It's more subtle than in the relativistic case, as Niels also mentioned at the end of his talk. So what you can do is, in this non-relativistic string theory, you have two distinguished directions. So you have difference between longitudinal and transversal directions. So you can do T-duality along both of them. If you do it along a transversal direction, you find that non-relativistic string theory maps to non-relativistic string theory. If you do it along a longitudinal direction, you actually find that it maps to the DLCQ of string theory. So you really find that it maps to relativistic string theory on a background with a null-killing vector. So that's slightly subtle. You can indeed start considering various compactifications and so on, and try to build up a whole web of T-dualities. You can ask yourself the question whether, so far we've only considered P equals 0 and P equals 1 supergravities, but it's natural to think that that one can try to construct supergravities for arbitrary values of P. You can really ask yourself the question, does there exist a whole web of dualities that relates all of these to each other? So far, these things have not been explored that much.
Okay, one last question.
Yeah, maybe it's related to what you have said. In the relativistic theory, we have the universal space-time with a certain geometry on which all these dynamical objects live, like particles, strings, brains. Here, it's as far as I understood, each dynamical object has its own geometry where it can live. Mm-hmm. So the question is what it means conceptually. For example, if you take the intersection of a string with some p-brane, what kind of geometry? Can it coexist, for example, in more complicated cases?
Well, that's a good question. So as I said, so far these things have not been explored that much yet, unfortunately. My personal expectation is that it should be possible to still find something that you could call a p-brane solution or a remnant of a p-brane solution in, for instance, like a p equals 1 stringy supergravity theory. And vice versa. If you have like various p-brane supergravity theories, you should be able to find like all the other, or remnants of all the other branes as solutions. But again, so far we have not really explored this in full detail.
Okay, let's thank Jan for his talk.
Quick announcement. We are having coffee break now, and the posters are all there. So since we didn't have a poster session, you should take the time to have a look at the posters during the break and the lunch break. And the poster presenters, after they get their well-deserved coffee, they could try to stand by their poster so that they can explain it to people who are interested. And the colleagues from the core group that I have graciously agreed to evaluate the posters, because let me remind you there is a €600 poster prize for this poster session. Before tax. So nothing after. Well, I have prepared for you a recap sheet, so if you want to take it, you can just come here and take it, and there are also pens, so just stop by. Okay, that's it. Enjoy. Ti ho mandato un invito.
Yes,
I think
I'll
I
do
might.
like
yeah,
this.
yeah, I think I might have a bit too much material.
So please sit down to begin. So the next speaker is Magdalena, please.
Thank you very much.
Machine learning tools for string theory.
Right, so let me first thank the organizers for putting together this wonderful meeting and giving me the opportunity to speak. So I will talk about machine learning and string theory, so how we can use machine learning in string theory. And this is a field that, where the first papers emerged some 7 years ago now, I think. So it's becoming more mature as a topic, but there's still a lot of unsolved problems, and there are still a lot of areas of string theory where machine learning tools have not been applied. So what I'll do today is that I'll talk around work that I've done together with the people mentioned here, so Larry Anderson, James Gray, Jakub Hendy, Andrei Lucas, Fabian Rühle, Robin Schneider, and Moritz Wange. And the work that I've been doing is in the context of string compactification and deals with geometrical questions related to string theory in that context. But what I want to do is to convey to you that these tools can be applied outside of this field. So in order to do that, I've tried to sort of explain how we think about how to use machine learning tools in this setting. And I'd be very interested to discuss with you after the talk and also during the breaks about problems that you might have, and if you're looking for new tools on how to attack them, please come and talk to me, and we can see if we can, if I can give you some information about some references or so that could be interesting for you to look at. But to start, let's start with some motivational problems. So I was motivated to enter the field of machine learning and to start studying this by my then PhD student, Robin Schneider, who thought that these were excellent tools to explore the string landscape. So a problem that has been driving the use of machine learning in string theory has been to try to build or study vacua of string theory from string compactifications that have certain properties and use machine learning as a tool to achieve such vacua. So to help in the calculations that you need to do, the computations, the analysis that you need to do, and this will be the main focus of this talk. But one can also apply it elsewhere. So one could imagine using machine learning for the swampland program. So thinking about whether machine learning could help build, analyze, or classify UV complete effective field theories like the one we heard discussed yesterday in Irina's very nice talk. Machine learning has also been used to do numerical computations of interest for string theory, both in the setting of the conformal bootstrap and in the geometric setting that I'm interested in computing Ricci-flat Calabi-Yau metrics. Machine learning can be used to learn mathematical structures, which may be of relevance for physics, and one can also turn the problem around and try to use physics and math to understand machine learning and why it works as well as it does. So there's progress of all of these topics, there's literature on all of these topics, and of course I cannot cover all in the 25 minutes that I have. So I will direct you to, in particular, this review by Fabian Rühle from a couple of years ago here. It's a physics report, it's quite long, and it has a lot of material, both describing the methods that people have been using and the kind of problems that they have been studying up to that time. So this is really a great introduction to the field. There are also some more topical reviews that are listed here, which go into more details, more specifics than Fabian's review. So why do we want to do machine learning? Well, the main reason is that it works. It can detect images of cats, and it can, now I'm going too far, and it can play games. And it does so it can beat humans at tasks that we would like to do, basically. So it may be that we want to play some complicated game like Go, or we may want to automate some task. We may want to label lots of images saying what's on them. We may want to have some translation from one language to another, and you can use machine learning for this. And these recent successes have been driven by a lot of different achievements in the field of machine learning. So there's better software, the neural networks that are designed today, their architecture is much more efficient, the optimizers are better, the hardware is better, there is more data and more money for training, and there are, if you want to get into this field, it's good to know that there are also very user-friendly libraries that you can use in order to study the kind of problems that you want to study. And at the core of most of these methods are neural networks, so some sort of algorithm that process some data that you feed into the system to give you some output at the end. And it does so by these kind of structures here, which are called neural networks. So in theoretical physics or in math, what can we do with these kind of tools? Well, first of all, we need some data, and a reason why people have started studying this in the field of string compactifications is that there we had data sets already available. So we had the huge data sets of Calabi-Yau manifolds that could be studied using machine learning tools. So by studying this data, machine learning can help us to find patterns, a bit like in the swampland, when you want to find a swampland conjecture, you want to study many, many examples and you want to find some pattern. You can do similar things with other kind of mathematical or physical data. Using these patterns, you can gain some intuition and make some conjectures. And then you can use that information to go on and study the problems and solve the problems that you want to study. And machine learning can also be a tool that we can use to speed up computations that we want to do. So in the setting then of the string landscape where we want to build string vacua, here we need to do computations that are related to the topology and geometry of the extra dimensions, and these are often hard. Even if we have methods for doing them, it may not be that we can always practically perform the calculations that are needed to be done. So these are algorithmic computations that we do on the computers already, but they may just run out of memory or run out of resources, and then these standard methods fail. So we can try then to use machine learning as a way of bypassing that kind of problem. So how does this work? Well, a simple example, the first example that was explored in the string theory community, as far as I know, is to try to use supervised learning. So that's a technique of machine learning where you know you have your data set, which has some input. In the case here, it would be some images of cats and other animals. Then you translate these images into a pixel matrix. You feed this matrix, sorry, I'm really bad at pointing with this thing. You feed this matrix into a neural network, and then you train this network on a data set where you know both the input and the output. And by training, the network learns how to classify whether this is a cat or a dog or a cow or so, with some given coordinates. So this is a prototypical example of machine learning. You do image classification via a pixel matrix. And this is interesting for Calabi-Yau topology because Calabi-Yau manifolds are encoded as integer matrices as well. So we can take our Calabi-Yau manifold and we can encode it in its configuration matrix. So this is a CC, and it's you have an integer matrix of some sort. You may have Calabi-Yau constructed in some other way, and then the matrix will represent something else. But basically, it's a matrix with integers. And you can feed this into the same kind of machine learning tools that exist for image classifications, and you can predict the Hodge numbers of this manifold from the configuration matrix. And this is not magic in any way. I mean, we know that the topological information is there in the configuration matrix because it carries that information. We know how to compute these things using algebraic geometry. What happens here is that we bypass those routines that we would need to use and use these machine learning recognition methods instead. So you can reach very high precision by doing this. On the other hand, this might seem a bit uninteresting because we already know these Hodge numbers, so we might want to look into some problems that were not known instead. And this has been done. So using similar kind of techniques, you can go to look at other topological numbers associated with string compactifications and Calabi-Yau. So for example, I've studied vector bundles or line bundles over Calabi-Yau manifolds where we are interested in knowing their cohomology dimensions because that feeds into different kinds of physics models that uses these kind of constructions. And then with machine learning, several groups of people studied this using different kinds of tools, and this led to a detection of different, of a pattern where these Hodge numbers are described by some analytical formulae that can be learned then using machine learning. And this has some interesting structure here, where M0 and M1 here are the charges of a line bundle over a particular Calabi-Yau, and one can find these regions in this charge space where there are some simple polynomial describing what the Hodge number would be, what the cohomology dimension would be for this line bundle. And the same kind of techniques have been applied in other kinds of geometric settings. So that's topology. We can learn topology from machine learning, and we can use that to detect some patterns. Another thing that we might be interested in doing is to use machine learning for Calabi-Yau geometry. So Calabi-Yau manifolds are famously known to admit Ricci-flat metrics, but also famously we do not know what the expression for that metric is. Excuse me. So we know from the Calabi-Yau theorem that such a metric should exist, and it's unique in any given Kähler class, but we do not have an expression for it. So the question then is whether we can use machine learning as a way of numerically computing this metric, and the answer is yes. So the idea then for this method is that there is certain information about these Calabi-Yau geometries, these Calabi-Yau metrics that we know. So we have access to a reference metric or a reference Kähler form of different types So it's not hard to write down a metric on a Calabi-Yau manifold. What is hard is to write down the Ritchie flat metric. So we can take some other reference metric that we know, and then we know by the Calabi-Yau theorem that the metric that we're after, which is Ritchie flat, it will be related to this reference metric by an exact addition of an exact term, which can be written in this way, and phi here is a global function. So then we can translate the existence of this Ritchie flat metric into solving this Monge-Ampere equation for the function phi. So this gives a second order PDE for phi, which is hard. It's usually we're interested in 6-dimensional spaces, those are compact. So it's not easy to solve this, but it's better than just trying to impose the Ritchie flatness condition on the metric directly. So what we can do then is that we can sample points on our Calabi-Yau, and we know how to do that now for basically any kind of Calabi-Yau. We can compute these reference forms. So J I already mentioned. Omega here is the holomorphic top form, which we can, given how we construct the Calabi-Yau, we know this information. And then we can solve the Monge-Ampere equation for phi numerically. And this is something that people have thought about before using machine learning. So there are methods from about 20 years ago now, where the first ones, where you numerically solve for these metrics using certain algorithms. So Donaldson proposed an algorithm for doing this, where you expand the function that you're after, phi, in a basis of functions, which are given as of polynomials on your Calabi-Yau. So there's some polynomial basis, and then the order of this polynomial will determine the accuracy of your numerical prediction, and then you can solve this problem order by order in this accuracy parameter, the order of the polynomial basis. So this has been explored using different kinds of techniques, some fixed point iteration scheme and some functional minimization. And it leads to very good predictions on very particular types of Calabi-Yaus. So the problem was it was solved basically, but only for specific types of Calabi-Yaus. And these Calabi-Yaus, where this method worked, are the ones that have a high degree of symmetry, so that the basis that you expand in does not become too large. So you want to go to high order in K, but then the degree of K also is K also sets the degree of the polynomial, so you get very many polynomials if you go to high Ks. So machine learning methods then allow us to bypass this, and this is something that has been studied by a lot of people over the past 5 years. And the methods work more or less like this. So the idea is that you take your point sample, you've sampled the points on your Calabi-Yau, say 100,000 points. You also have the moduli of the Calabi-Yau, which determines what kind of geometry you actually have. And then you feed this as input into a neural network of this very simple form here. So it can be some simple neural network with maybe a bit wider than this one. Maybe you want some 100 nodes or some 60 nodes in your in every layer of your network, but you don't need a lot of layers. You don't need deep neural networks for this. You can work with quite shallow neural networks, and you can achieve the same performance as you have for this fixed point iteration scheme by training these kind of networks for about half an hour or even 10 minutes on your personal computer or your laptop. Whereas with these numerical methods as we had before, you really had to use much more computational resources to work even on these simple manifolds, and going to more complicated Calabi-Yaus was just out of the question. So because of the simplicity of these networks here, or maybe because of that, we don't really know why it works so well, this kind of method works for many different kinds of Calabi-Yaus. And what this network does is that it outputs the Calabi-Yau caliform and the Calabi-Yau metric for you. So the metric is really encoded in this neural network. So the neural network is your approximative Ritchie flat Calabi-Yau metric. And how does this work then? Well, you set up your network and then you encode the constraints that this metric should satisfy, for example, Ritchie flatness, or being globally defined, or being Kähler, depending on how you set up the problem. And then you train the network using the standard routines of machine learning, and you check performance afterwards. So you have some error measures that you check on some test data sets. So you have your training set of data, and then you have some unexplored points in your Calabi-Yau where you check whether things work or not. So there's a lot of work also ongoing on this, and there's work on improving the accuracy and performance of this, including moduli dependence is something that people are very interested in particular complex structure moduli dependence. Kähler is a bit more hard, I can explain why. And then, of course, using these for physics and math is something that has been starting to appear in the literature in the past year and in this year. Okay, so these were two ways of using machine learning in string theory, and it's a kind of, finding new ways of performing computations that we already knew how to do. So in the last 5 minutes or so that I have, I will go into talking about search tools that we get from machine learning. So if we want to search the string landscape for nice vacua, what kind of methods are they? And there are a couple of methods. I will focus on one of them, which is known as reinforcement learning. So reinforcement learning is the technique that was behind machine learning beating the world champion of Go a couple of years back. The idea of reinforcement learning is that you have, there are neural networks in the game, but they are not really visible. So you have an agent here, and the agent is observing an environment. It could be the Go board or some other environment. The agent is in a state in the environment, so it has some configuration on the Go board, and then it will take an action, so it will swip some pieces. Actually, I don't know how you play Go, so it will do something with these black and white marbles. I don't really know. And then it will get into a new state, and if that's a good state, it will get a positive reward, and if it's a bad state, it will get a negative reward. And it will learn from doing this many, many times what are the good things to do. So the idea then is that you train the network to learn how to win this game or to solve the environment by receiving rewards. And this has proven to work well in large environments and also with imperfect information. And these are two things that we need to deal with in the string theory landscape. So we don't know everything about the string theory landscape, and we also don't expect to be able to explore it completely because it's so large. Now, importantly, in this method, there is no approximation. So the two methods that I talked about before, there you have some, you make a prediction with some certain accuracy. There's an uncertainty there. Or with the Calabi-Yau metrics that you compute, that's a numerical approximation. There's an error in there. But here in reinforcement learning, you don't really approximate anything. You just look for new solutions. And you train the network, or you train your agent to find these solutions. And the way that you do that is that the agent will take decisions based on a policy, and that policy will be a neural network. That is the thing that you train. So you get really exact solutions from this, and you can also discover new strategies for how to do things, how to search for how to solve, how to win games, and how to search for new string vacua. So then, if you want to use this method in string theory, then you need to think about, okay, what kind of problems can I turn into a game of this sort, where I know the environment, I know the kind of actions that I can take, and I know I can set up a reward structure for how this should work. And this has been used in different kinds of string compactification. So in the first paper on this was intersecting brain models in 2019, and then it has been used for heterodic standard models, type-Debye flux vacua, conformal bootstrap, and also knot theory, maybe not really string theory, but it kind of fits here because of the people who have done it. And the idea then is that you have this agent who is absorbing this environment, which will then be the string theory setup or the physics setup that you're interested in, and you set up some states, or you know the states of this. So the state in a string theory compactification setting would be, okay, what kind of Calabi-Yau manifold do I have? What kind of vector bundle over that Calabi-Yau manifold do I have? And then the reward would be based on whether this configuration satisfies, giving a a particle physics model with 3 matter generations, for example, or the gauge group of the standard model. So this is one method for doing this, reinforcement learning, and there are other methods. One is known as genetic algorithms. I will not describe it, but you can see in some of these papers that they compare with that method, and they have different characteristics and different pros and cons, so it's good to be aware of both. Okay, so here are some experiments that I did with my PhD student, Robin, and what I wanted to show in this slide is not so much that we could plot things, but rather that we could explore different kinds of actions in this environment that we were studying, and the strategies so these correspond to different strategies that you take for exploring your string landscape. They are outperforming random walkers, both of these strategies. This one here, which is different from a systematic scan, so very different from what you would imagine doing as a human, is really, really good at outperforming the random walker. So it gives you some new way of thinking with the problem, how you should work with it. And also because with reinforcement learning, you need not systematically explore all vacua of your string landscape. You can just go for the interesting ones. This means that you can reduce the time that you spend on computing things, and this means that you can go to regions of parameter space that were not explorable before. Okay, so let me wrap up. To conclude, I hope I have convinced you that yes, machine learning methods can help string theory. We can bypass hard computations, we can detect new patterns, and we can improve numerical approximations using these methods. So if you want to use this yourself, I would also like to give you this little roadmap here. So I think I'll just leave this for you to read and say thank you for listening.
Questions?
Thanks. It's a question about new patterns. Can you give an example of some type of new unexpected patterns that were noticed thanks to machine learning? Well, question, do there exist new patterns that were noticed thanks to machine learning, and what are they?
Yes, there are. So this pattern with the line bundle cohomologies, it was expected. So that was not completely new. It had been observed in some examples, and with machine learning, one could see it more broadly. There have been patterns observed that go beyond our field. So to be honest, I'm not sure I could pinpoint some discovery in string theory that has come from machine learning yet. But there was a famous paper from last year in knot theory where they managed to detect some patterns about that led to a theorem, some inequality that could actually be proven, and that was not known before. So it was a relation between different invariants, algebraic and geometric invariants of knots, and that relation was not known before. So it has helped. But it's really, it's not like you just, feed some data to the algorithm and then it spits out something at you. You really need to work with the data, and you need to analyze and try to really condense the information that you get. So if you have some neural network that has been trained and that predicts something, then maybe you want to do some pruning of that neural network to see if you can cut away some things and get some clearer patterns that you can then analyze and make some conjecture from.
Other questions?
Thank you for your talk. So you've mentioned the connection to string theory. What about some other problems, such as, I don't know, scattering, particle physics, and so on? How much has this been explored?
It has not been explored that much, but I know that people are thinking about it. So I expect that there will be publications.
Thank you.
Any other questions? Yes.
I was wondering, can you use this to try and find beyond Calabi-Yau compactifications,
Yes.
or like back-reacted flux?
Yes, you can. Some of these Calabi-Yau metric networks, the ones that I've been working on, they are designed in such a way that you can generalize them to go beyond Calabi-Yaus. And this is work in progress, really. So no one has. There's actually one paper where they find Strominger-Hull solutions using the same methods. But beyond that, it hasn't really been explored. But I think it should.
Thanks.
Anyone else? Okay, let's thank the speaker again for the nice talk. So the next speaker is Kobi Sonnenschein. Chaos in string scattering.
Okay, so I first would like to thank Sandro and the rest of the organizers for inviting me to come to this very exciting meeting.
Use the microphone.
Okay. So I'll talk about chaos in string theory and beyond, and it's work that I've been doing in the last 2 or 3 years with Massimo Bianchi from Rome, and Maurizio Firota, who is now in Crete. Doreen Weissman is in the Asia Pacific Center for Theoretical Physics in Korea. Let's see, so which one goes straight? Let's see. So what is here forward? This one. Oh.
This goes back. This goes forward.
Okay, so I'm a physicist and I'm starting my research project always with some experimental data. So the data here is some observation that was made by David Gross and Vladimir Rosenhaus, where they analyzed this process of decay of a high excited state into 2 tachyons, and they observed that the amplitude, this decay amplitude, is quite erratic in the sense that if you look on the amplitude as a function, I have to find where is this. Okay, so this is the amplitude as a function of some angle. I'll describe it in details later, but you see that it looks very erratic, and moreover, if you compare these 2 pictures now, the decays of a state of level n, which are quite similar but somewhat different in the sense that some of these construction of the states have different partitioning. This will have n11, n7, and n5 equal to 1, and this will be n12, n6, and the rest are similar. So by small changing of the partitioning of this high excited state, you get a very different erratic behavior of the amplitude. It doesn't fit my finger, so this one. It did. Okay. Okay, so that is another example of a level of n equal to 100, and This is the log of the amplitude. You see that it behaves in an erratic way. And again, if you change the partitioning in these two tables, you get the structure of this logarithmic derivative of the amplitude to be quite different and erratic. Oh, come on. Maybe you can. Okay, in the middle, okay. So this is another example of such a decay. So it's an excited state that decays into tachyon. It's now n equal to 100. I just, flash these pictures to so that you see that they are really, this is string theory where the levels are very precise, no chaotic signature of the levels, but nevertheless, the decay looks very erratic. And okay, so now I went. Well, I'm going over all the Hmm? The lower part is so the upper is big.
I think it goes over, the lower goes backward.
Okay. Okay, now I got it. Okay. Maybe you change it for me. My fingers are not. Oh. No, that's very different. Maybe I'll bring my laptop and. So meanwhile, I'll maybe it doesn't have battery. Okay, so meanwhile, I'll tell you without the transparencies. So there are two obvious questions coming from these kind of pictures. One is what is the source of this chaotic behavior? And the other one is how to quantify it. So David Gross and Vladimir, they had these erratic pictures, but they didn't have a clue of how to decide whether they are really chaotic and in what sense they are chaotic. And so this second question of given an amplitude which looks erratic, how can you quantify it and check whether it's indeed chaotic? And that was our project. So basically the novel idea was to use what people previously, starting with Wigner and Dyson, did for... okay, so this is for... So I have to go back to the beginning. Sorry about it. Okay, I've been here. Okay, so now, as I said, there are these two questions, and we will address this question of how to quantify this story of erratic amplitudes. Now, the basic new idea that we had is that we want to map the amplitude into the random matrix theory. And the question is, in random matrix theory, the basic ingredient are the eigenvalues of the random matrices. And so the question, with a given amplitude, what do you map to this random matrix eigenvalues? And our idea was that we take the locations of the peaks of the amplitude, namely the zeros of the logarithmic derivative of the amplitude. Then we map them to the random matrix, and then we ask questions that are being asked in random matrix theory, whether these amplitudes also obey these properties. So these are the zeros of the logarithmic derivative, and this one, these zi's, will be mapped into they will be mapped into the eigenvalues of random matrices, more precisely to the so-called beta ensemble. So the way that there are several measures to use to play with these eigenvalues. One of them is this spacing. So you take adjacent spacing delta n. For instance, for this Hamiltonian system, it's En plus 1 minus En. And then you discuss these ratios, delta n plus 1 over delta n. And from the distribution function of these properties, the spacing and the ratios, you can check whether the corresponding function is chaotic, and more precisely, what particular value of beta it has. So as I said, in our case, we replace these eigenvalues of the matrices with the locations of the peaks. And the general idea that we came with is that similar to what Wing Dyson suggested many years ago, to map energy eigenvalues to the random matrix eigenvalues. And mathematicians did it for instance, the zeros of the Riemann zeta function and zeros of other special functions. We propose to take this location of the maxima of scattering amplitudes. I'll demonstrate it in three main examples, but it can be generalized to any scattering amplitude, in fact. Okay, so I'll say 2 words about this beta ensemble, this random matrices. So the beta ensemble is defined by this joint probability distribution. So the probability of having eigenvalues from lambda 1 to lambda L is given by this expression of e to the minus beta over 2 lambda I squared, and this van der Monde determinant. And for the particular values of beta equal to 1, we are in a GOE. Or beta equal to 2, we are in GUE. So this is Gaussian orthogonal ensemble, this is Gaussian unitary ensemble, and this is Gaussian symplectic for beta equal to 4. And the main point here is that we can explore it for general beta, not necessarily one of these particular one. And you give me an amplitude, I'll go and analyze and tell you what is the beta that it corresponds to. And in this sense, what is the form or structure of the chaotic behavior. Okay, this is the way which is used to parameterize this beta ensemble with normal distribution, normal functions along the diagonal, and chi distributions along the off diagonal. I won't go into the details. and similar to what Wigner had for this GOE. GOE relates to time reversal, so that was that was the case for this heavy nucleus states that he analyzed, and the point is that the density of the eigenvalues behaves like a semi-circle. That's is very famous. Similarly, one can define the cumulative distribution, which is just the integral for minus infinity to lambda of lambda prime, and that is given by that. And in that case, we discuss the bare spectrum, and here we discuss this unfolded spectrum. Okay, and there is an explicit expression for the probability of this ratio. So R, for instance, for cerebral matrix will be lambda 3 minus lambda 2 over lambda 2 minus lambda 1, and as a given of beta, this is the expression that one should get. And this is, of course, invariant under R goes to 1 over R. Now, one of the new concepts that we came with is to take the so-called spectral form factor and define instead a scattering form factor. So the idea is basically to start with the ordinary partition function and with the spectral form factor, the usual one, which we take for beta tilde, the inverse of the temperature to 0, and it's just a sum over n over m e to the I t e m minus e n, and we will replace it by a new parameter, we call it s, which is not the time, and this location of the peak. Okay, so as I mentioned before, we can go from this discrete set of eigenvalues to the spectrum to a continuous density of these eigenvalues, and in that case, we will get that a chaotic system is characterized by 3 regions, and the region follows from the fact that this scattering form factor, or also the ordinary spectral form factor, they have in general 2 main parts: the one, the disconnected one, which is this, and the one which is the connected one. Now, if we go to the region of, small t, or in our case small s, then we will find out that it's just the disconnected part that contributes, and it's easy to see that in that case it will behave like 1 over s to the third, or 1 over s squared if instead of this semicircle we take a constant. And so there is a region of this decline. I had this picture, I'll have it again, and there is a region of a ramp, which is sometimes it's linear ramp for GUE, but in general there is a ramp which is characterized by this sine kernel, and there is a region which is the plateau. So altogether, we have, no, I want to go backwards. It's crazy. Okay, so this is the general structure of this scattering form factor. This is for an interesting demonstration of the zeros of zeta function. So either we take an average of 2,000 sets of each of them with L equal to 100 zeros, or the opposite. So you see that there are 3 regions, decline, and this linear slope here with in the ramp. It's linear because it's GUE, and the plateau. And the question that we were asking is that structure also what we will see when we take scattering amplitudes? That's totally not obvious that it will follow this behavior. Okay, so what we've done, we started with, well, let me go first to this example, which I don't have much time to describe, but before going to string amplitudes, we looked on the so-called phase shifts from a leaky torus. So you start with a torus with such a cusp, and if there is a wave coming from the y equal to infinity at the end of the cusp, and you look on the phase shifts, then it was analyzed by Gutzwiller, and it was found that the phase shifts behave like a ratio of zeta functions. So clearly you get peaks when you will have zeros of the zeta function, and one analyze it by this so-called Wigner time delay, which is thus the derivative of the phase shifts. And when you look at that, then for this case of this leaky toes, we can both look on the spacing. So these are the normalized spacing, and, and this is the normalized ratio. And you can see that if it fits quite well this Gaussian, this GOE. I mean, this is a case which is time reversal invariant. So indeed, we see that the spacing or the spacing ratio fits for this case, which is also the case for the Riemann zeta function. Because of the formula that I showed you, we get quite good fit. I mean, our idea was to find exactly what is the best fit in terms of beta, which is not necessarily 1 or 2. And we found out the precise values that give the best fit. But basically, it is in good agreement with these random matrix theories. Now, as I told you at the beginning, the original experiment that drove us into this game was this high-excited string states, so-called DDF states. So what is a DDF state? You start with a tachyon, and and you shine on it. You let it interact with a sequence of parallel photons with a momenta q. So you take m of them, then we have that p1 tilde goes into this with n times this q with an angle beta. And then if we define this alpha, which is the angle here in the decay, minus this angle of the photons, that is the alpha for which the amplitude were shown to exhibit this chaotic behavior. So I will skip some of the details, but we can write explicitly. This is the expertise of my collaborators, Massimo Bianchi and Maurizio Firota. They know very well this story of how to compute these amplitudes. And after some mathematical steps, we get that the amplitude behaves like this expression where Gn is the multiplicity of applying a equation operator alpha minus n. And this is our angle here. And if you look on this expression, and you first go into this logarithmic derivative, that then we find out, I'll show you in a second, that it admits indeed the measures of the ratio and also the SFF, very similar to GUE. Now, the other thing that we did was not only a decay, but rather a scattering, or differently, a decaying of a high-excited state into 3 tachyons. So again, we have the expression. I won't go into all the details, but we know the amplitudes, and we can check their behavior as a function of the angle. Here it's a real angle in the scattering, and we can do it in both this Reger regime is much greater than t, or in the fixed angle in the fixed angle regime. So, and this was the fixed angle, and this is the Reger, and we first look on this ratio of the spacing, this R tilde, and again you see that there is a fairly good agreement with the beta ensemble. In fact, we get that the best fit is for beta not equal to 2, but rather 2.27, and we then analyzed and we understood the limit of beta going to 2 using different higher levels of states, and we've done the same also for the decay processes. So if we now want to look on this scattering form factor, then for a while we were confused because you see on top of this decline, ramp, and plateau, one gets also this bump, and we didn't know how to account this bump, but then eventually we found out that if one does appropriately the unfolding by averaging separately unfolding of several states and then averaging of them, then it goes away and one get a very clear and nice behavior. This is, for instance, for n equal to 20,000, sorry, and so you can see here the decline, the ramp. People played a lot with this in the SYK model, but here it comes out from a totally different notion of scattering or decays of strings. So this is, again, some examples with 20,000 and 40,000, and you can compare it to this CUE, or which is also the GUE. So you see it's not, the black line is not precisely what is the best fit, but rather the yellow line, which has some shift relative to this GUE or CUE. Now, this is something that we haven't published yet, and that is the so-called Montgomery pair correlation. So one can also discuss the correlators of pair of these eigenvalues. Now in the GUE, in the random matrix, it behaves like this sine kernel. That is very well known. Now Montgomery conjectured that also the zeros of the Riemann zeta function will follow such a behavior. And it took quite a long time before this guy, or this go, did the numerical calculation and find indeed that, well, this is with 10 to the 5 zeros of the zeta function. You see that it follows quite nicely this basic sine kernel. And I think that this is the first time that anybody did it also for this string scattering amplitude. So we found that also in our case, when we took a very high excited states, we get these pair correlators, which is very similar to this thing kernel. So let me summarize what we've seen. We've seen that the decays and scattering of DDF high excited states admit chaotic behavior with a particular value of beta. And we found out the precise beta as a function of this level n and so on. Of course, when you do it for the first Regge trajectory or for low n, you will not see any chaotic behavior. You have to go to very high excited states. And the ratio of the adjacent spacing and the scattering form factor, this is a notion that we invented, the scattering form factor. And now also this pair correlation function, they seem to agree quite nicely with the random matrix here with beta, which is not precisely 2, but close to 2. So let me tell you what are some future directions that we are now following. Of course, one want to do it for a general scattering and decays of high excited states, not necessarily these high excited states go to tachyons, but it could be high excited states go to HES prime plus HES double prime and so on. Now we can, we showed this erratic behavior as a function of the angle. We shift a little bit the angle and the behavior is very different, but there are other kinematical, basically in 2 to 2 it's SNT, but otherwise for higher point functions there are other kinematical variables for which there should be some regions of chaotic behavior. Now I'm coming back to physics, so why should I care about these high excited string states? And so one of the things is that using holography and the so-called Polchinski-Strassler prescription of going from flat space scattering to scattering in QCD, for instance, if you take the appropriate holographic background, then one would expect that if we do some high excited proton and we look on the scattering of it to a lower excited proton plus a pion, this will also admit some chaotic behavior. And of course, one way to approach is to take these stringy amplitudes and take the limit of alpha pion goes to 0. Now, again, the question is what physics domains this may be relevant. I think personally that if one goes back to the very early universe, then there should be chaotic processes there, and well, this may change the way that we view the evolution of the very early universe. Now, it's also interesting that this kind of a map and analysis can be applied to other erratic functions which are not necessarily related to string scattering or not to string at all or not to physics at all. So you give me some erratic behavior, I don't know, for population growth or weather or whatever, and we can try and do this game of mapping it into the random matrix theory and exploring its chaotic behavior. So it looks to me that it has a potential of quite a lot of applications. Thank you.
Questions?
For a heavy excited string state, there are many decay channels. You consider the decay channel into two tachyons, which is the less dominant one. Most dominant will be, say, a decay into another massive state by a soft emission of something.
N over 2 plus N over 2. That will be probably the most...
Yeah, so the question is why you consider the less dominant channel?
Because we know these amplitudes and we could analyze them. I mean, it's much more complicated to get these other amplitudes, but once we have it, and I know that the group in Crete and both you are working also on these other amplitudes, and once we have an amplitude, it's very easy to check it. Okay. It's very difficult to get the amplitudes.
So this value of beta, it's really not 2, right? That's like a 5 sigma reliable statement.
Right.
And the value is robust 2.27 regardless of the value of n and so on. It's really...
No, it is sensitive to n.
Oh, it is.
So when we go to higher n, we are coming close to beta equal to 2 for both the ratios and the SFF.
Ah, good. Because otherwise it would be very strange.
Well, it's not very strange, you know, because there is a lot of stuff entering in this.
Yeah, but if you think...
and stuff like that,
but you would think that if you take some large n limit or something, that you should land on one of these standard ensembles.
Yes.
Because those are protected by symmetries, and anything else would...
What we expect, and we want to check it by computing this. So, I mean, related to your work of chaotic decays of black holes, this black hole string correspondence should relate this type of analysis also to some processes of the black holes.
But you see it decaying at large n too. Yeah, okay, thanks.
Yes.
I have just wondered, you have demonstrated n particle hundreds system. If you take the 1,000, what you expect? Because you mentioned that the tachyons, if we assume the infinite system, so what will be happen? Because you said that if you change one or two things, so this shifts. Exactly.
Two questions. One question is about this erratic as a function of n. And
yes.
It's clear that for low n it's not erratic, and we have to go to higher n. As we go, as higher we get it more erratic. Now the other question is this dependence on the partitioning,
yes.
which by the way does not exist in, for instance, in the Hamiltonian system.
Yes.
But that is okay. So now I'm coming to this second question. What is the reason that there is a chaotic behavior? And this, by the way, I think will be also in quantum field theory that people recently started to analyze. What happens here is that you have a system with a very high degeneracy. So such a state of n equal to 100 or 40,000 have many positionings, which are all with the same level. They are, of course, not with the same helicity. I didn't mention it, but it's not processes that the helicity is concerned because there's superposition of many states with different helicity. But in any case, once you start with such a state, and the state itself is not chaotic at all. You know, it's very simple. You take alpha to the -1 to the power ng, or alpha minus n, and so on. These are the partitionings. So how comes that the spectrum is totally non-chaotic, but the scattering is? And the reason for that is that when we talk about the spectrum, we talk about the spectrum at the tree level. And we didn't took into account loops in the spectrum, which will make it getting some widths and so on. So in the spectrum, it's a tree level, and in a sense, G string is 0. But once you do the scattering, there is no scattering, G string is 0. So you have to turn on a small string coupling. Now this coupling destroys the degeneracy. And then the small changes may cause different dramatic effects. So this is, we didn't prove it rigorously, but we believe that that's the source of this chaotic behavior, the fact that there is a very high degeneracy, and which can be lifted when you turn on a small string coupling.
Okay, thank you.
Any more questions? If not, let's thank the speaker again. I think it's lunchtime.
It was a party.
You're the boss?
I'm the boss. This is the pointer. Just try it. It works. But, just to get familiar with the pointer. The thing on top, it works with the gyroscope. So you don't need to point towards the screen. You can point whenever you want. And sometimes it's better not to point towards there because then it works weird. But well, you can try. Okay. Very important. Unfortunately, they don't have.
Yes, I have to hold. Like, is the mic there? Like,
Yes.
you
So
can
if you
turn
stand
that
here. Yeah. Test. Yeah. This
on?
works.
Okay. I might just do that.
But remember that if you move, then
Yeah.
they will not hear you.
So is that on already, or the mic, the one you're holding, is it on?
Yes. Well, now not. But this works. Do you want one?
So that I'm not a way to pull it down, but if I'm just standing in the podium, then it's more.
If you stand there, because the point is that they are recording the.
Yes, no, I.
And if you don't
If you
speak
want,
in the
I'll
microphone-
keep it. I'll keep it close to me. Let's see how it goes. But I'll mostly be like this. You can hear me.
Here you have the slides.
No. No. What about now? Can you hear me? No. Yes. Yeah. No. Okay.
Do you want me to tell you how much?
What about
time is
now?
left?
But it says, if I do that, okay? Not okay. Fine.
Do you want me to tell you how much time you
I'll
have
just
left?
give you
or
Yes, please.
like
Because
10 and 5 minutes?
10 and 5 minutes is amazing.
Okay, please take a seat. So it's time to start the afternoon session. And the first speaker now is Alejandra Castro from Cambridge, and she will tell us about engineering gravitational theories in ADS-CFT. Please.
Okay, thank you. Thank you so much for the invitation. I might start doing this throughout the talk.
But I'll tell you.
Please, yes. Remind me to keep my mic near to my mouth. I'm not used to talking in this way. But in any case, thank you for the organizers for asking me to give a vision of what I think is interesting, is exciting, and, well, of course, related to the stuff that I do. So that's what I'm going to attempt today. I warn you already, I will prompt it throughout the presentation. I think I prepared too much. But it's okay. So if I don't get to cover everything, the slides will be available online, yes? And so then you can look at what the topics maybe that I didn't cover. But okay, so let's get started. So what is the idea that I have in mind? So at the center of what I'm going to be telling you today is the gravitational path integral. Okay, so as we all know, this is basically an object that I've written here formally as something where you're integrating over all possible geometries and topologies. So over the gravitational degrees of freedoms, you will have fields involved, and they will be weighted by their action, and there's going to be basically some boundary condition that you're going to put on this object. Now, in recent years, this has been revisiting this object, quantifying it, computing it, has been incredibly productive. So in particular, two things that it has been quite useful at are basically underlying, for instance, the microstate description of black holes, computing black hole entropy, reproducing the page curve, quite surprisingly. So although this object has been introduced by many decades by now, it's only recently that we know that there's actually a lot to learn about gravitational path integrals, more than we expected. Now, one of the lessons, and here's where I will start also making connections with other visions that we heard yesterday, is that there's cases actually, very simple models, where we can compute this path integral exactly. okay? And one of the cases, so this is for instance 2D gravity, 2D JT gravity is one of the most famous cases nowadays, is that when you have access of doing an exact computation, the way that you have to think about the answer that you get is in terms of a coarse grading, okay? So you don't get a density of states that is compatible with a discrete spectrum. You get something that looks basically like that curve. You get like a spectral density. And so in connection to what Jan was basically guiding yesterday, there's this coarse-grained picture of how do you think about quantum gravity. But I am of a more discrete mindset. And so what I want to do is take a different perspective. So I want to say, let's imagine for a moment that I know what quantum gravity is. Okay, that we have a candidate. I'm a string theorist, so I'm confident to say that I can pretend that this is something I know. Okay, so in that case, you will have some discrete spectrum, as I'm trying to kind of cartoon here. So there will be some discrete set of eigenstates. It will look chaotic, that's fine. But there was going to be something that I should be able to compute, in particular, like something like trace of e to the minus beta h. Okay, now, even if I believe that there's a theory in quantum gravity, there's a UV framework for which this is true. One of the open questions is basically, can we derive this in detail? From here, can we derive the gravitational path integral in detail? Okay? So can I make a very specific and precise connection between these two concepts? This is what I want. Okay? This is what I think it's an important question to ask in a theory of, in a UV complete theory of quantum gravity. Now, you would say, for instance, in the context of ADS-CFT, is that the answer we're expecting, we have the belief that, yes, there should be a situation where this is possible, because when we have backgrounds that arise from string theory, there's a single Hamiltonian in these dualities, and you should, in principle, see that trace of e to the minus beta h is equal to a gravitational path integral, right? But we don't know actually how this emerges, okay? So there's not a simple example where you explicitly compute a trace and you see it exactly as a gravitational path integral, okay? We have a lot of indications and hopes, but it is not something that you would say, yes, we have derived the gravitational path integral from this discrete spectrum. But I already see an objection to that statement. Or what's that?
Our question is allowed at this point. Okay.
What's that?
No, it's okay. So, but isn't it the gravity supposed to be a low effective description? And I mean, you shouldn't expect exact equality.
Quantum gravity as something that has a UV description.
Yes, but you don't expect that doing the path integral over low energy degrees of freedom will give you the exact answer.
You will have to add, like that's the point.
Yeah.
Like how do you see basically, in some sense, if you're telling me that there's a duality, there's an equality between two things, both sides have to be well defined, right? And so from the perspective of ADS-CFT, one side of that equation you're quite comfortable with, right? You do not object to computing the trace over the Hilbert space in a CFT. What is the gravitational computation that you're supposed to do on the ADS?
No, I mean, philosophically, I agree, but just the formula seems to me too naive, but okay. Yeah.
The other side of the equation is what I mean by quantum gravity. That will mean for me that I understood what quantum gravity is. If I can't make sense of that other side of that equation, I would not admit to knowing what quantum gravity is. So that's part of like the vision. We want to know what quantum gravity is. Okay. But we're not there yet. I think this is not something that we would feel like comfortable at establishing, that we understand how this, if you want, starting from that trace, basically, how do you get to this low energy description systematically, case by case? This is something that is, we don't understand. We have indirect evidence. There's pieces where we think that this is true, but it's not like a direct computation. And so this gets at the questions of basically what are the rules controlling the gravitational path integral in these cases? Because cases where we can compute the gravitational path integral, we don't get this answer. So there should be some differences, there should be some modifications. And something else that is important that I will highlight as we go along is that if I only have gravitational degrees of freedom, metric degrees of freedom, I don't think we're going to get to this discrete basically description. And so there has to be an interesting interplay about how gravity talks to matter and how maybe there's modifications there in order for me to get this discrete spectrum. So what I want to do during this presentation is basically give you three sharper questions because how I presented it to you and how it's already illustrated by the reaction is maybe set up in a way that is too broad. So I want to narrow it to three more specific questions of what do I think are useful ways in understanding this equation. So the first question is basically in the context of ADS-CFT, so I'm always going to be talking about it in the context of ADS-CFT, is basically trying to understand what are CFTs that can capture classical properties of gravity. Okay, so we have many examples, but they're examples. I don't want examples, I want mechanisms. I want rules, I want classifications. Second, are there consistency conditions for the CFT that have an imprint in the gravitational path integral? So are there things that we can detect, that we can learn from the CFT, and they will tell us, this gravitational path integral has to reproduce these answers, and it gives us basically an understanding of what are possible effective field theories. And I'll show you an example of this. And then the last question is basically, given a CFT, how do you organize it such that quantum gravity is manifest? Okay, so how do we rearrange things in a way that it pushes us forward? And so yesterday I was going through these three questions, and I ordered them in this way here in this slide, but then when I was organizing the rest of my slides, it's like, which one should I explain first? I'm not going to have enough time to go through all of them. And so I made an executive decision, and we're going to start with the last one, okay? So we're going to first ask, given a conformal field theory, how can you organize it such that quantum gravity is manifest, okay? So that you can start seeing the hints of this gravitational path integral that, as you go along. And so, okay, so let's start with number 3. So let's just pick as an example, this is old work that I've done, but I want to illustrate the point. Let's just grab two CFTs that are well known, they're solvable, they're loved by condensed matter physicists. So let's pick the Ising model and the tricritical Ising model, okay? So the Ising model at the critical point is a CFT with central charge equal to 1/2. The tricritical Ising model is at the critical point, it will have central charge 7/10, okay? These are CFTs that are solved. There's everything that you want to know about them, they're known. And in particular, something that you know about them, that you can open the Francesco, go to the appropriate chapter, the partition function is exactly known. And how I'm writing it here for each of these theories, I'm favoring basically how do you organize the spectrum in terms of Virasoro representations. So there I'm basically have a sum over the allowed primaries, and there's a character associated to each primary, okay? Known system, solved, done. Is this gravitational? How do I see gravity from these examples? And so you might ask the question in the way that I was asking at before, is there a way how I can rearrange this partition function such that it looks like a path integral over metrics? And so before I tell you what the answer to that question, we should think about what does it mean for it to look gravitational, right? So it's a question like, how do you see gravity manifest itself in this type of situations? And in this case, because I have a two-dimensional CFT, the question is in ADS-3 gravity. And in ADS-3 gravity, at least from a saddle point of view, I know what are Euclidean solutions that will contribute. So you start with a cylinder, Lorentzian ADS, you make time periodic, so that introduces a beta, and we know that there's various saddles that contribute, such as thermal ADS and the BT set, and they're related by basically a modular transformation. Here I just illustrated one, the S transform, but in general you have a whole family of modular images of these saddle points. And so the expectation from a gravitational point of view, if you only have metric degrees of freedom, is that this path integral, as you compute it, should be organized as a sum over images of the vacuum contribution, where the vacuum contribution is basically the contribution that comes from thermal ADS, and that the images will give you basically the black holes. So this is what we expect roughly from a gravitational path integral. So okay, that's the lamppost. Does the Ising model and the tricritical Ising model allow a rewriting in this way? And the answer is yes. Okay? It's not how you would write it. You're not going to find this in DiFrancesco. They're going to write it as the first line. But you can actually write it for these two cases. You can actually rewrite that partition function as a sum over images. Okay? So this is just as a thought example, as a toy model of like, what do I mean by asking you rewrite things in a way where gravity might become more manifest, okay? So in the first equation, I'm favoring Virasoro symmetry. In the second equation, I'm favoring basically the saddle point of view, okay? That's basically the contrast between the two of them. You're not losing information, but it's just basically giving you a different perspective on how you interpret the model. Now, of course, this toy model it's really toyish. It's not great. There's a question.
How can you expect to have for C, which is not large n, duality with gravity?
It's remarkable,
and
right?
Not with the full string theory. And also, where is the strong coupling in this game?
Well, this is related to my remarks and why this might just be viewed as an academic exercise. Because, for any minimal model, you can always write a version of this, but it will not be the vacuum character that you're summing over images. It will be something else. But basically, just to be clear, these two minimal models are the ones that admit this very specific characterization. In the next slide, I'll tell you how it generalizes to other rational CFTs. I'm coming to your question. The reason why this is not like a great maybe lesson for ADS CFT is that the value of the central charge is fixed, right? And it's really low. And so I don't have anything else to say about that. Like, it's not like, that's why there's no large n here. N is 1/2. So I think it will be interesting to see, like, well, I don't know, is the Ising model part of the string landscape? I guess yes.
You work with string theory, but not to gravity.
Right, it will be a string theory, fine. But it's kind of interesting that you already see some hints of what that string theory, that theory of quantum gravity, why would it be amenable to it? And so why could you maybe formulate a duality for this system in this case? But in any case, this is basically like a big drawback of what I'm showing to you here. But more has happened, so these are all results. They're more than 10 years old. But recently what happens now and nowadays is that the way that I think that you should be thinking forward is like try to rethink how you organize your quantities in a CFT. So because we read DiFrancesco, we like to think of it in terms of like this number of primaries and these characters. But there's been recent developments. I'm putting here some references for you so you can look at those papers where they say, okay, don't write your CFT partition function necessarily in that way, okay? So one way how you maybe want to write it is have a decomposition for something that will have an arbitrary value of central charge, something C bigger than 1, where you have a part that is a sum over images, and it's images over the light part of the spectrum with an appropriate definition of what it means to be light. And then there's a spectral part of the answer. And the spectral part, for instance, related to what Jan was talking about yesterday, this is the part that is going to contain your chaos, okay? This is the part that is going to be perhaps compatible with like this random matrix type behavior. But this is basically a push to say, reorganize your way of thinking, reorganize your structures, try to think about CFTs in a different way, okay, such that maybe these coarse or chaotic features come about. Now, it has two motivations besides ADS CFT. Well, there's one motivation that it comes like, if you start organizing CFT partition functions in this way, it will give you a nice interplay about like how quantum gravity plays with quantum matter, what are the rules in this GPI and how do you quantify it. But also, it should be said that we're terrible at classifying CFTs, that have central charge bigger than 1. And so that first equality is not actually very useful. We've not been able to bootstrap CFTs that are irrational, in a sense, by taking this Virasoro perspective. And so a way, if you don't care that much about quantum gravity, but because you care about the space of conformal field theories, this might be a useful way also how you might want to solve for the conformal bootstrap, and how you might want to think further about what does it mean to describe one of these like very strongly coupled, very chaotic and messy CFTs. And what gravity in some sense is maybe telling you, 10 minutes, okay, is that you really need to rethink how you organize the structures. Okay, but maybe you're like, no, I don't want to think about CFTs in terms of new observables. I want to organize them as I go. Fine, so let's go to the first question that I had, and let's take maybe a more traditional point of view of how would you go about in understanding what does it mean for a CFT to be holographic. So now, when I talk about holographic CFTs for the rest of this part, I really mean holographic here will mean that it's a CFT whose gravity dual has a low energy effective field theory description. So to satisfy Kobe's question, like I'm now interested in these large N CFTs. I'll move away from the Ising model. And so what we know from ADS CFT is that there are a few properties associated to these CFTs. So we know we need large values of the central charge if you want this low energy description. You want a sparse spectrum. Basically, in the language of the CFT, you don't want a lot of light operators. You want this generalized free field behavior, so you want a factorization of correlation functions. And there's more properties that you might associate. But something that I think should be very much recognized in the community is that there's a reason why I didn't write a full list, because these are things that we know happen in examples, we know that they're important, but I don't know if these are basically sufficient conditions, or if they're merely necessary. And how stringent are the conditions? Maybe if I impose a couple of them, I will already get the other ones for free, or not. Okay? So the interplay between these conditions are not fully understood. And basically, the question that I want to address here is, can we engineer CFTs that satisfy these criteria? So if I ask you, build for me a CFT that complies with this, that are not the ones that we know already from string theory, can you do it? And so to illustrate that this is not like an impossible question, this is where my engineering hat comes on. It's like, okay, so let's build those CFTs. So what do? You have to pick a material. What we picked, we said, let's look at symmetric product orbifolds. So these are basically, I'm not going to give you a whole lecture on this, but there in that corner, I wrote a very short definition of what I mean by symmetric product orbifold. Tensoring a theory and modding it out by the symmetric group. Now, these are theories that we picked because they have a lot of mathematical and analytic control. They're familiar. One of the examples shows up in the D1, D5 CFTs. They have very compelling features for ADS CFTs. And their large M behavior seems to be quite robust. Okay? And so then you can ask the question, which of these symmetric product orbifolds could admit in their moduli space basically a point where you would have a dual supergravity description. Okay? And so the strategy is basically, let's start imposing conditions to see if I should call any of these examples something that is connected to a holographic CFT. So the picture that we have in mind is basically the following. So symmetric product orbifolds, for various reasons, they appear as like the weakly coupled description in your moduli space. So there will be like, if you want, the tensionless limit of the string theory. But then there should be a marginal deformation that in principle should have a strongly coupled point, and that's where you're going to see your theory of gravity. So the question is, if you grab any symmetric product orbifold, can you basically establish the existence of that strongly coupled point? And the answer, so we basically then here draw our universe of all possible symmetric product orbifolds for simplicity, let's just talk about supersymmetric cases, because there I actually know what I mean by a moduli space. And you can ask, okay, so how many of them do you think have this strongly coupled point in their moduli space? The answer, most of them won't, okay? So most symmetric product orbifolds don't have a strongly coupled point, and that we could detect from the elliptic genera. So by computing the elliptic genera in these cases, we saw it's a protected quantity. It will not be compatible with having a holographic CFT. But there are two, what we did spotted some non-trivial features here. So it's not all gone, because we know that, for instance, D1, D5 is there. So there should be at least some positive cases. And there's actually two like little spots in this space, in this swampland of green. And so the first spot, the red one, is basically symmetric product orbifolds where you do have basically a protected deformation. 5 minutes, yeah. I will not go through the third topic. And you also have a sparse spectrum in the elliptic genera. Now, a condition to be in that red region is that the central charge of what you put here in one of the copies has to be less than 6. And lucky you, D1, D5 sits exactly at C equals 6. So string theory was at the edge of that classification. But then we quantified for lower values between 1 and 6, we quantified what are other CFTs that meet the same criteria as the D1, D5 CFT, and there's many of them. In particular, there's a whole class of any n equal 2 Virasoro minimal model will satisfy these two cases, and then we also have a whole list of examples between 3 and 6. Okay? But now, because I'm running short on time, let's go through the second corner here. And the second corner is also interesting because this is a case where you also have a moduli space. You will have a marginal deformation that is basically of the same nature as I was describing before, but these symmetric product orbifolds do have a Hagendorn behavior. So these will be examples that will never have a holographic point. But what this teaches you is that, for instance, having this moduli space is not enough to guarantee a holographic CFT. So you need more than demanding that you have a suitable coupling that you can turn on. But also, it also seems like every time that we were complying with a sparseness condition, the moduli space came for free, in a sense. So this illustrates like what is the stringingness, like how stringent is one condition versus another. And so then the task here, so I think this exercise illustrates the point, and I ran out of time probably, is that we can basically, if we pick our materials appropriately, we can really try to understand what are differences between different CFTs. And this whole discussion has just been from the CFT point of view. And so if you want, a challenge is, tell me if I imposed enough conditions. Did I have sufficient conditions? I impose conditions that are necessary, but it's not clear that they're sufficient. So can you build the gravity dual of these, or the string dual? Go for it. And if you can't, it's great, because then we will learn that there's a more stringent condition. That there's actually, I have to impose something else, and that will lead to something that will have a connection to gravity. And so this is part of understanding the mechanism of why these examples work or not. Okay, so I'm at -2 seconds, -3 seconds, and -4. Okay, great. So I'll, this one was about actually, this is the last question that I had, is that if there are consistency conditions in the CFT that have an imprint in the GPI, and this actually brings me back to black holes, and again, supersymmetric black holes, where we're much better at computing the path integral. And it actually relates to an index in the CFT. And we're also quite good at computing indices in the CFT. And in this case, actually, what's interesting to look at is the quantum corrections of the black hole. So maybe let me just go to since I don't have enough time, to this version of the side. So we're mostly used to like looking at just the area of the black hole. But from the gravitational path integral, you can also get the logarithmic correction to the area. And there's a counterpart derivation of that from the point of view of the microscopic description. And in cases, explicit instances of the correspondence, people have worked really hard on doing both sides of this computation. And there is an agreement, okay? There's a very nice agreement between these two sides. But there's also something interesting that happens here. And let's take a case of ADS4 black holes. So what I want to illustrate here is that, for instance, if your EFT is 11-dimensional supergravity, and you compute this logarithmic correction, so Marcos can tell you all about how you compute that logarithmic correction, it's something that is just a rational number, like it's integer, half integer, and it's a quite simple thing, like, well, you still have to be careful, you can get the integer wrong, but it's just a number. Now, if you do it from a perspective of ADS4, and you just have a finite number of fields in this EFT, this logarithmic correction is going to depend on the parameters of the black hole in a non-trivial way. It's not going to be a rational number. And the thing that is curious that I like to highlight is that at least every time someone has computed this logarithmic correction from an index, I have never seen an example where that coefficient depends on ratios of charges. And so you can guess here what this can teach us. This can teach us something, for instance, about scale separations in ADS-CFT. This can tell us you cannot UV complete a theory of quantum gravity in ADS4 if you just have finitely numbered fields. Of course, this side here, what we really need to have, it's a better understanding what I'm highlighting in green there in the bottom. We really need to understand what is the meaning of that logarithmic correction in the CFT and establish if it's always something that is independent of the parameters, or maybe there are CFTs that I'm just not familiar with, where this thing maybe can depend on the ratios. And it's just a coincidence of where I'm looking in ADS-CFT that they happen to be very simple things. So with that, I'll conclude. Done? So these were the 3 questions that I presented very quickly. And I put here underneath each of them basically either 2 aspects or 2 further sub-questions that I think will be interesting to pursue. And I hope members of this collaboration might find this fun to work on. So, done. So think out of the page, like in an ADS-CFT, you're at the boundary, go explore the bulk, come back.
We have a question.
Not funny enough.
Yeah, so you were looking at constraints on the CFT that might lead to a theory of quantum gravity, but in the last few years there have been several proposals for actually quantum gravity, at least have a low energy effective description of quantum gravity corresponding to an ensemble average over CFTs.
Yeah.
So,
yes.
Is there a particular reason for expecting,
no, so that's
single
why
CFT being a very good description of quantum gravity in arbitrary dimensions?
Well, okay, it depends. Okay, so this is why I started with what happens if you just compute a gravitational path integral. So if you just compute a gravitational path integral in solvable models of gravity, then you don't get this discrete properties. You get the spectral density, which is the ensemble description that you're. So when I wrote down that curve, that's what it meant. That if you get like a spectral density, you're getting on usually it's interpreted as some type of coarse graining or ensemble. And the example is an ensemble over theories. In general, just to be honest, like it's not always clear what you're coarse graining over. So that's also a big important open question in the field, like what are you coarse graining over? But okay, in the case of JT gravity, it's Hamiltonians. But in some sense, I don't think that's the end of the story. Because what I learned from string theory is that there should be cases where the spectrum is discrete. And so I just decided, because it's my vision, that I want to focus on those cases where I'm expecting from the UV a discrete spectrum. And then what does that tell me about the effective gravitational description? So what do I need to modify from this low energy point of view such that I get that picture? So how do I resolve the factorization problem? How do I resolve all these features that seem to not be compatible with it? Because I do think that there is a landscape of gravitational theories, and this is where it connects also with what Irene was saying, that there should be a landscape of effective field theories of gravity that do admit a UV completion, and this is basically very aligned with what she was saying yesterday. What are these theories of quantum gravity that have a UV completion? And by UV completion, I mean I want my thing to be discrete. It can be chaotic, it will be strongly coupled, but please, let's keep it discrete. And yeah. But yeah. Any case, we can chat later about like the other perspective if you want to push this ensemble average interpretation.
More questions?
Very nice talk. So you promised that you make a comment why higher minimal models don't have gravity duals. And then maybe I missed this point.
Yeah, it's because, let me go back to that slide. They will have a gravitational interpretation, but not in terms of pure gravity. So it will be something that will have more stuff in it. So any minimal model, so let me point to this equation because it's a bit more general here. So for any rational CFT, you will always be able to write the partition function in this way. This spectral part is going to be trivial. It's going to be exactly 0. But what your image is, the C light, is not the vacuum character, and that's what I meant by pure gravity. So the seed that you put in there is a combination of basically every state that it's polar, basically. It's between minus C over 24 and 0. And so I'm putting the vacuum at minus C over 24. And so any primary that is between minus C over 24 and 0 is what I'm calling light. And that from if you can still interpret it gravitationally, but it will be a theory that will not just be pure gravity, it will be gravity plus matter. And so that's what I meant in the previous slide, that because in the previous slide, I did write vacuum as the seed, and that's very, very specific to these two models. And it's because these two models are the only minimal models that don't have a primary between minus C over 24 and 0. So the C light here is actually the vacuum character, but any other minimal model will have a few states in between.
And is it possible to test this with some other observable, not the partition function, but some correlation function?
Well, then it's a little bit more tricky for the objections that I had, that then I'm a little bit more nervous what I mean by quantum gravity. But there has been papers, follow-ups, where they did higher genus Riemann functions. Riemann surfaces. And so there's been some follow-up since there. Actually, from the condensed matter community, there was some interest in reorganizing these things in this way. So there's I can point to you to some papers that came after, but it was like the higher genus partition functions.
Okay, so I would post very quick and a very quick answer.
I'm sorry.
Thank you for your talk. So in this talk, you've posed the question which CFTs may have a gravity dual, if I understood properly. I would like to ask the reverse question. What gravitational theories may have a CFT dual? Is it an equivalent question?
In a sense, it's a bit equivalent, but this is where I think you need a synergy between the two sides. So I think there has to be push on on both sides. But right now, I'm hoping, my perspective is that I think the CFT can teach us a bit more on like, when we add matter, maybe what do you expect the matter to interplay with gravity such that you start seeing some of these things get erased or removed. But it will come from a little bit from both sides. But right now, yeah, I was pushing more the CFT. Just because I know that I'm starting with a discrete spectrum from the get-go.
Okay, it's a bit late, so let's postpone further discussions for the coffee break, and let's thank Alejandra again. So you can either speak in this microphone or with this, but it's important that you always give it this, of course. And you have the pointer. Oh, I have the slide. Do you want me to tell you about time or do you? No. So with this you go forward and with this you go back and this is good. No, it wasn't. It takes a second. The next to skip. Okay. Let's see.
And
Right.
it works with a gyroscope, so you don't need to point at it.
For the next one. You need for
Yeah,
forward and
also
backwards.
the pointer.
I'll work it out. I have a PhD.
All right. Okay. Our next speaker is Emmanuel Malek. He will tell us about recent advances in supergravity and puzzles for ADCFT. Please.
Okay. Thank you very much. So this talk is a little bit of a mirror of Alejandra's talk, very much coming from the supergravity side and trying to see, using some recent techniques we've developed, trying to see some new features in CFT, and also, as you will see, some strange things that we don't understand that I think fit very well into this workshop. So the ADS-CFT correspondence really tells us that we can use string theory to perform computations to learn about strongly coupled CFTs, and a very nice target for what to compute are 2-point and 3-point functions of the CFT. In principle, if I have the 2-point and 3-point functions, I can get all the other correlation functions using OPEs. Having said that, despite several decades, 20-ish years of ADS-CFT, computing the 2-point and 3-point functions has remained very, very difficult in the supergravity side, and in particular has only been possible when the backgrounds are very symmetric, in particular maximally supersymmetric ADS backgrounds. One of the reasons why this is so difficult is because, in particular, some of the 2-point functions are no longer protected by supersymmetry if you're not maximally supersymmetric. And so this makes it also very interesting. This really pushes you away from the many techniques that have been developed which focus on really supersymmetry, protected observables, supersymmetric indices, and so on. To get these kinds of computations in non-trivial examples with less supersymmetry, we really cannot rely on supersymmetry at all. So in particular, 5-ish years ago with Henning Samtleben, we sat at a workshop similar to this, a very nice workshop, and we thought, okay, well, what do we need to do to actually compute these objects? And this talk is very much about the road that this led us on and the kinds of techniques that we developed. And in particular, one of the nice things has been that we've really come across some very interesting features in CFTs, and there's been a bunch of puzzles. Okay, so what do we actually need to compute in the supergravity to obtain the 2-point and 3-point functions? Well, firstly, CFTs are very nice because we have so much symmetry, so the 2-point functions are completely determined up to a number, the conformal dimension. So how do I compute the conformal dimensions in supergravity? Well, it turns out the conformal dimensions are just related to the masses of my fields in supergravity. That's nice. But I have infinitely many fields in supergravity because I'm looking at some kind of ADS compactification, so some ADS times some compact space, typically some sort of sphere. So I get infinitely many fields organized in Kaluza-Klein towers. So the question then comes, how do we compute these Kaluza-Klein masses? You can ask the same questions about the 3-point functions. I'll come back to these at the end of the talk. The 3-point functions in the CFT are defined up to just a number, some kind of structure constants. And it turns out these structure constants you can basically read off from the cubic couplings in supergravity between all of these Kaluza-Klein fluctuations. So understanding these Kaluza-Klein fluctuations is important. Now, if you've only ever done this in your master's course, you think it's very simple. This is what you would normally do. You take a massless scalar field, for example, or Minkowski times a circle. Let S1, the y-coordinate be the coordinate on S1, x the coordinates on the Minkowski space. Well, this is the free scalar field equation. Because I'm working on S1, I can just do a Fourier series in the y-coordinate. And then everything is very simple. The Fourier modes are eigenmodes of the Laplacian on the circle, which is just the second derivative. And so I immediately find the usual mass relation in terms of the eigenmodes. Okay, this is very nice. Why is this more complicated in supergravity? Well, because the theory is much harder. So in supergravity, I have complicated equations of motions, mixing the metric and the fluxes. And for the masses, I only have to work with the linearized equations of motions, but still, these are very complicated. Just to remind you how complicated these are, this is one of the equations of motions you get in 11D supergravity, where you have a background four-form flux, a background metric that I haven't written explicitly, but is in the connections and raising and lowering indices. And then I also have four-form fluctuations and metric fluctuations, little h. So this would be the linearized equation of motion. And then you have to try and understand what are eigenmodes of this. This is extremely difficult. And as a result, this has only been possible for two very special cases until recently. The first case is where I only look at the Kaluza-Klein tower spin 2 fields, and the other case is where I look at very, very symmetric examples, so where the compactification is a coset. And in particular, this had an interesting application in ADS-CFT in the early years, even working with T11, which is such a coset space where you can indeed use group theory to compute all of these. But for more general backgrounds, there's nothing, there used to be nothing you could do. But then Henning Samtleben and I, we came to this problem from a very different perspective. We came from the area of consistent truncations, which allow you to compute these masses for a subset of the Kaluza-Klein fluctuations. So what are these consistent truncations? Well, a consistent truncation is where I keep only a finite subset of fluctuations around some backgrounds, only finitely many fields. I get some lower dimensional theory, but I want to keep these fields in a full nonlinear fashion. Then I have some lower dimensional theory with some potential that I can study. Okay, so far so good. But now, because I'm keeping some modes and getting rid of other modes, I'm not guaranteed that solutions of this low dimensional theory have anything to do with my original theory. So a consistent truncation is a truncation where I keep the subset of fields in a clever way such that all of the solutions of my low dimensional theory are solutions of the original theory. If I do this, then I can compute the subset of masses that I've kept in the truncation for any of these solutions. As an example, this works for type 2b supergravity on around ADS 5 times S5. This would be, because it's just around S5, we can compute the full Kaluza-Klein tower. And it turns out there's a consistent truncation where I just keep these three sets of modes encircled here in red. These define some 42 scalar fields. This would be the potential of these 42 scalar fields. This is just some subslice. And there is a consistent truncation, meaning that any solution of this potential corresponds to some solution in 10-dimensional supergravity where the 5 sphere is deformed in some interesting way. And in particular, because I've kept some modes in the truncation, I can compute what happens to the 42 scalar fields that I've kept in the truncation as I deform the 5 sphere. But in principle, you would think I lose all the information about the other Kaluza-Klein modes that I've not kept in the truncation. But it turns out, as Henning Samtleben and I realized, these consistent truncations have very nice geometric properties, and these nice geometric properties allow us to actually recover all of the information about the higher KK modes that you get rid of in the consistent truncation. And so you can use these nice geometric structures that these backgrounds have to compute all of the KK towers and their masses and their interactions for a variety of examples. And to do this, you have to use something known as exceptional field theory that I want to just quickly tell you about. Okay. So how do you construct these consistent truncations? Well, we want to perform some truncation where I keep a subset of modes of some lower dimensional theory, and I want to embed these modes into the full 10 or 11D supergravity in some complicated way, such that all the solutions of the lower theory are solutions of the original theory. This is very difficult, and whenever things get difficult in physics, we rely on symmetry, and it's the same thing here. We'll have to use some symmetry arguments, and the symmetry arguments that we're going to use are left invariance arguments using group manifolds. So if I have a group manifold, then I have two very nice things that make this procedure straightforward. I have a global frame, my left invariant frame, and moreover, because of left invariance, this frame closes into an algebra under the Lie derivative. So if I take the Lie derivative of two left invariant vector fields, I get the structure constants of the Lie algebra of my group. And it's very easy to show that if I have these two properties, I can define a consistent truncation where I expand all of the fields of my theory in my basis of left invariant fields, or my global frame, and the coefficients will be fields of the lower dimensional theory, and these will define a consistent truncation. So this is very nice, except for the fact that group manifolds are kind of boring. So we'd like to do something more interesting. And before I get to supergravity, there's a very instructive example that shows that actually this can be generalized. So consider the following theory. It consists of gravity, so I have an Einstein-Hilbert action, I have a scalar field, and I have a Maxwell field, and there's a non-minimal coupling between the scalar field and the Maxwell field with this coefficient alpha, that's just some number, that I can choose. It turns out when I choose this number correctly, there is a consistent truncation of this theory on a two-sphere to some lower dimensional theory. And this is quite miraculous. S2 is definitely not a group manifold, so it doesn't seem to fit into the previous picture. There's no symmetry argument that tells you that the modes you've kept will define a consistent truncation. And moreover, the truncation ansatz is a complete mess and was really a miracle that it was found in 2000. So what is going on? Well, it turns out for this particular value of alpha, where you can define this truncation, this theory of Einstein-Maxwell-Dilaton is actually just GR in one higher dimension. This is just the usual Kaluza-Klein theory. And then it turns out, okay, I'm actually doing consistent truncation not just on S2, but on S1 times S2. But if you look carefully, the truncation actually involved a flux of the Maxwell field through the S2. So this is not even a product, it's actually a fibration. And in fact, this S1 times S2 turns out to be the Hopf fibration of S3. And then you can understand what's going on. I'm actually performing consistent truncation in this larger theory, GR in one higher dimension, on a group manifold S3. And so now I have a global frame, and this global frame defines an algebra, and the consistent truncation is very easy. I just expand in my global frame. So what's the lesson here? The lesson is that I shouldn't take my Einstein theory with Maxwell and Dilaton fields and view them as separately. Rather, I should unify all of these fields into some larger geometric framework, in this case just GR in one higher dimension. And then in this larger geometric framework, this is where I should look for a group manifold, and it turns out there's a group manifold and hence a consistent truncation. So how can I use this for supergravity? In supergravity, I don't have Maxwell fields typically, I have some larger fluxes like 7-form fluxes. Well, it turns out there is a way to do this, and there's a way to unify all of these fields, the metric and the p-form fluxes in supergravity, into some larger notion of geometry, and this is known as exceptional field theory or generalized geometry. And the reason for the exceptional is because basically the groups that then act on this larger space turns out to be the exceptional groups. The details are not super important, but then you can actually recover all of these consistent truncations that were known, for example, since the 80s, the 11D supergravity truncation on S7 to 4-dimensional maximal supergravity, but also a bunch of other ones. And the picture is like before. Now, rather than working with the fields of 10 or 11-dimensional supergravity, where the truncations are very miraculous, it turns out that if I rewrite these theories and unify all of the fields into my larger geometry in exceptional field theory, then there is some generalization of a notion of a group manifold, which allows me to define a consistent truncation. In particular, what do I have? I have a global frame now of this larger geometry, so some generalized frame if you want, and this global frame closes into an algebra using the notion of Lie derivative that exists in the theory, which is known as a generalized Lie derivative. And then because of these two features, I can expand everything in my global frame, and I can easily show that I get a consistent truncation. Okay. So this is all nice. What does this have to do with ADS-CFT correspondence? It turns out that certainly all of the maximally supersymmetric backgrounds, like ADS 4 times S7, ADS 5 times S5, but also many other ones define exactly such generalized group manifolds in this exceptional field theory. So in particular, I can describe the round spheres and these generalized group manifolds, and these have nice geometric properties. But also all of the deformations within the consistent truncation still have these very nice structures. And this is really powerful because these deformations might now break all kinds of symmetries and supersymmetries. They might be warped. They might look very complicated. but in this exceptional field theory language, they still have this very nice group structure which allows us to perform non-trivial computations. Okay, so how can we now compute the two-point functions of the CFT? Well, this is now very straightforward. We have two important features, as I said. We have these generalized group manifolds, which means in particular we have a global frame. The global frame means that we can expand all objects in our particular basis defined by the frame. And then I just need to worry about coefficients. So these are all going to be scalar objects. So I only need to use scalar harmonics. This should be contrasted with what I would normally do, where I would take all of the fields of supergravity and expand them in appropriate tensorial harmonics. So for example, the metric, I would have to expand in symmetric 2-tensor harmonics. 3 forms, I would expand in some 3-form harmonics. In this exceptional field theory language, everything is much simpler. I just need scalar harmonics because I have my global frame. Then I have this fact that I have some notion of left invariance because I have this notion of group manifold. And exactly like on a group manifold, this means that all of the differential properties become reduced to structures at a point. For a group manifold, I know that all the structures on the tangent bundle I can reduce to the Lie algebraic identity. Similarly here, because of this left invariant, I can reduce everything to a point. And so in particular, computing things like eigenfunctions and eigenvalues of differential equations reduces to an algebraic problem now of just computing eigenvectors and eigenvalues of algebraic matrices. So this becomes much, much simpler. And then the final point that's very nice for us is that all of these deformations are deformations of round spheres. And so what should we use as these scalar harmonics? Well, we can just use the harmonics of the round spheres. These are the same topological spaces. And it turns out this basis for the round sphere is actually extremely useful for us. And so all of this computation has become very straightforward. So now let me show you what you can do with this. My first example will be, again, related to ADS 5 times S5. So I have, of course, the maximally supersymmetric ADS 5 times S5 vacuum, dual to n equals to 4 super Yang-Mills. I have a consistent truncation on S5 with some interesting potential. This potential, with 42 scalar fields, turns out to have one supersymmetric vacuum. And this supersymmetric vacuum preserves just a quarter of the supersymmetries. And it breaks SO6 to some SU2 flavor and U1 R symmetry. And in this CFT, this corresponds to some mass deformation of n equals to 4 super Yang-Mills. But now we have all of these nice tools, so we can in particular compute all of the two-point functions for all the single trace primary operators and compute their anomalous dimensions. And this is really quite striking. We can find in particular some closed form for the anomalous dimensions in this strongly coupled CFT for all of the single trace operators. And this is related to simply the charges of the symmetry groups that we have, things like the Lorentz group, the charge under the U1, the SU2 flavor charge. But also quite interestingly, we also get a relationship to the Kaluza-Klein level of the original 5 sphere. So this is already something puzzling from the CFT. Why do we have this relationship to the 5 sphere level? But in the supergravity, in the way we're doing it, this is completely normal. This is completely natural. Moreover, you see there's a square root in this formula. So for generic values of these charges, these conformal dimensions will be irrational, corresponding to unprotected operators. But for special values of these charges, the square root will disappear, and this will actually become the conformal dimensions of semi-short multiplets. And these you can then check with the usual ADS-CFT tools. You can compute the superconformal index for the CFT, and these exactly match on the nose. But then there's, from my perspective, the more interesting questions: what about the long operators? Can we develop new CFT tools to actually check the prediction here for the long operators, and to be able to actually see the conformal dimensions from the CFT computation? Or maybe even less ambitiously, why are there finite conformal dimensions for unprotected operators at strong coupling? This is a very strange thing from the CSP perspective, from the supergravity. This is something we immediately find for these less supersymmetric cases. So this is a puzzle that I want to leave with the audience. How come we have these finite conformal dimensions and strong coupling for unprotected operators? Okay. Let me show you some other things we can do. It turns out these Kaluza-Klein masses are really nice observables to actually study the geometry because they're gauge invariant. And this actually allows us to learn about the geometry in a much simpler way. To demonstrate this, consider the following example. There's some interesting 4D supergravity whose details are not important, but has two moduli, two directions in the 4D potential which are flat. I call these var phi and delta. For any value of var phi and delta, I have some n equals to 2 ADS4 vacuum. And in general, I have just very small isometries, U1 times U1. But for special values, I get symmetry enhancement or even supersymmetry enhancement. One of the puzzling features from the ADS-CFT perspective is that in supergravity, these moduli appear to be non-compact. The ADS4 vacuum seems to be different for any value of these two parameters, whereas from the CFT perspective, there's some general arguments that this space of conformal manifolds should be compact. So what could be going on? Well, you might say this 4D supergravity has nothing to do with string theory of quantum gravity. Maybe it can't be UV completed. But we can show that this does actually come from a consistent truncation. So this is some slice of type 2b supergravity or type 2b string theory on ADS4 times S5 times S1. And in particular, you can uplift, in principle, the full two-parameter family of ADS4 vacua to type 2b string theory. However, in practice, this is extremely difficult to do. So instead, what we did is to just study the Kaluza-Klein spectrum as a function of these moduli to try and better understand what's happening in the geometry. And we, for simplicity, just focused on one of the moduli, this var phi direction. So we looked at what happens to the Kaluza-Klein spectrum as I change var phi. And I'm showing you the result, the Kaluza-Klein spectrum as a function of var phi. And here I'm going to show you the lowest lying levels on the S1. And you see, indeed, var phi, as var phi increases, some things are independent of var phi and some masses increase, but there seems to be no periodicity. But now we can use the tools and compute higher Kaluza-Klein levels. And you see something interesting, that higher Kaluza-Klein masses actually become light as var phi increases before they become heavier again. And if I keep going to 10, this picture starts looking very nice, and if you stare at this for a few seconds, you notice it's very symmetric around this halfway point. In fact, you can show the Kaluza-Klein spectrum is exactly the same at this point, var phi is 0, as when var phi is shifted by 2 pi over r, where r is the radius of this circle in the background. So this suggests that actually maybe var phi should be compact because the Kaluza-Klein spectrum is periodic. And with this new insight, we could then go away and actually study the geometry, and we could show that indeed var phi is actually a compact modulus, but this is not seen in 4D. This is only when you include the higher Kaluza-Klein modes, and it's related to some complex structure deformation of the background. More interestingly, this is not something isolated to this ADS4 times S5 times S1 background. This happens whenever you have some ADS background times a compactification times S1. So as long as you have some S1 factor, you always have moduli of this type where you mix local U1s on the compactification with the S1. And in particular, depending on which U1s you choose, you can choose these moduli to be either supersymmetry preserving, like in this example, or even supersymmetry breaking. What's nice about the supersymmetry breaking moduli is that these have very nice properties. In particular, the ADS vacua are fully perturbatively stable, and they even seem to have nice mechanisms that protects them against other instabilities, in particular non-perturbative instabilities, alpha prime corrections, and so on. So one of the interesting questions I think coming out of this is, what is the fate of these non-supersymmetric moduli, which in the CFT should correspond to some exactly marginal deformations? Could we be having some exactly marginal deformations in CFT which are non-supersymmetric? Okay, and then finally, in the last minute or so, I want to extend this. This was all about 2-point functions. I told you I was going to talk about 3-point functions as well. It turns out we can actually do the discussion for general n-point functions. these are related to the endpoint couplings in supergravity, and we can show, because everything is controlled by scalar harmonics, that the supergravity couplings vanish whenever the scalar harmonics don't contain a singlet in their representation. So this integral has to be non-zero for the couplings to be non-zero. And what's very nice about this is it means that many, many more couplings vanish than you would expect based on the symmetries of your backgrounds. So just as an example, if I do this for ADS 5 times S5, even for the maximally supersymmetric background, you find that couplings vanish, which don't obviously need to vanish because of SO6. So for example, the chiral primaries transform in the symmetric tensor representation of the vector of SO6. So SO6 group theory would tell you if I have n of these, there has to be a singlet for the coupling to exist. So this gives you some condition, some kind of polygon condition on the Dynkin labels. But actually, this XFT analysis shows that many more couplings vanished. So for n points, whenever this condition is less than or equal to 2 times n minus 3 rather than just 0, we can show that these couplings vanish. And in particular, this proves some old conjectures about supergravity couplings by various people, including Boris, who is here, about near extremal couplings in supergravity. Even more interestingly, this means that infinitely many endpoint functions in the CFT vanish, even though the symmetry doesn't require them to vanish. So what is going on here? There seems to be some relation with having this consistent truncation, which allowed me to use scalar harmonics. And this leaves me on my final puzzle, which is what is the meaning of all these consistent truncations from the perspective of CFT? For us, it was very important that we had these consistent truncations to some maximal supergravity. That allowed us to perform many computations of supergravity. What is the meaning of all of this in CFT? How could I know that a CFT is part of some maximally supersymmetric truncation or not? In particular, the most naive thing you might think is that these are all going to be deformations of n equals to 4 super Young-Mills or ABJM. But that's not true. The consistent truncation doesn't need to have any vacuum that preserves all of the supersymmetries. It could be that all the vacua preserve some supersymmetry. So this is a very strange statement, even in supergravity. And I'd love to know, what does this mean from the CFT perspective? What makes these CFTs special? And let me end with that. Thank you.
Questions? Oh, sorry.
Just a very short one. I mean, we had an argument about n equals 2 near extremal correlators to vanish because of some charges when we had differentiated in the coupling. That was charge counting. But it's one of your list, I guess.
Yeah, the example I showed was ADS 5 times S5, and there is, as I mentioned, this n equals to 2. I mean, I should actually check. N equals to 2 for you is in the CFT or the ADS? Like
n equals to CFT, I mean, n equals to CFT.
Then, yes, so then, okay, I wouldn't be able to do this ADS5 example, but there's other examples. There's certainly lots of these near extremal couplings that would vanish, but this notion of near extremality is really something I think that becomes less useful for less supersymmetric backgrounds. So certainly there would be many, many couplings that vanish, some of which you would call near extremal, but also others, that's for sure. Yeah. But I don't have an argument for why from the CFT, if that's your question, only from the supergravity.
Yeah, no, I was just wondering whether you can pin out some kind of consistent truncation which would give you exactly that, but maybe we can...
Yeah, I mean, so the thing here is we're really finding that we're showing that infinitely many couplings vanish. So this is really beyond the consistent truncation. The consistent truncation would be like that couplings between finitely many fields and some other ones vanish, but here this is some generalization where even for higher Kaluza-Klein levels, you get relationships between couplings that vanish.
More questions? Yeah, coming.
You had several examples of non-critical dimension. For instance, this Einstein-Dilaton-Maxwell case. I mean, are you sure that these cases obey the vanishing of the one-loop beta function?
Yeah, the Einstein-Maxwell-Dilaton was really just a toy example. This doesn't even have an ADS vacuum, I don't think. So that's really just some toy example. But all of the other examples are real supergravity ones that are some low energy limit of string theories.
Well, it's obvious for the critical dimensions, but it was less obvious for the cases that it took non-critical dimensions.
Yeah, so apart from this Einstein-Maxwell-Dilaton, they were all always parts of a consistent truncation of 10 or 11D supergravity, so they were always critical.
Any other question? Then let's thank Manuel again. Thank you. So we come back at 15:50.
Sorry for running a bit.
It's good to be flexible.
Yeah, thanks.
option is that you
Yeah, I will try to use that one. Yeah, just in case it's there.
Yeah. Now it's off, and like this it's off. You can leave it here maybe or below. Or I can keep
Yeah.
it there. Okay, so let's start. Please take a seat. I'll wait 1 minute. I'll wait 1 minute. We are about to start. Okay, so we are now happy to have Zoltan Bajnok, and he will tell us about Tracy-Widom distribution in super Yang-Mills theories. Please.
Thank you very much. So let me start by thanking the organizers for the kind invitation and the opportunity to speak here. So I would like to report on results done in collaboration with Grisha Korchemsky and Bercel Bordisch. They are both in the audience. So you could feel like in the optometrist probably now. You can cover one of your eyes, and then you should tell me what is the coefficient of zeta 5 in the first column. If you can tell, then you are eligible to drive. So I'm presenting here 3 perturbative series. The first in QCD, in the strong coupling, running coupling. The second one is in the 2-dimensional O4 nonlinear sigma model, the free energy density. And the last one is a 4-point function in n equals 4 super Yang-Mills. What is common in these 3 perturbative series that they contain zeta functions, even and odd, some of them only odd, and sometimes log2s. And the expression why I actually needed to shrink the later and the larger perturbative corrections was because they grow. They are bigger and bigger because they can contain all possible zeta functions up to a given transcendentality. Unfortunately, in QCD, we cannot calculate actually many terms. We have only these 4 terms, and probably we will have only these 4 terms for 10 more years. But if we evaluate the numerical value, we can see that they grow. So instead of doing the calculation in QCD, we would like to do the calculation in a similar theory, and the 2-dimensional O and sigma models are very similar to QCD in the sense that they have a dynamically generated mass, and they are asymptotically free in perturbation theory. So in this theory, because this is an integrable theory, we can actually calculate a lot of perturbative coefficients, and then we can see how they grow. And they grow like factorial. We can do the same in this n equals 4 super Yang-Mills, and they also grow like factorial, and we expect that a similar factorial growth will appear also in QCD. So at the first part, I would like to teach you what you should do if you have an a perturbative series which is factorially divergent. And I would like to explain. So there are basically two parts. The first is about the O4 model, when I introduce the ideas and the final solution. And then we will switch to this ADS-CFT correspondence and the specific observable, a specific 4-point function, when I would like to repeat the same. This is not complete in the N equals 4 case, but it's complete in the O4 model. So what is the O4 model? We already had a talk actually yesterday about this O4 model. It's a sigma model. Maybe it's related to the next talk in this sense. So it's almost like a free boson. Yeah, I try to use. So it's almost like a free boson, except the field is restricted on the unit sphere. I'm not sure. Okay. So what we are going to do, so it's on the unit sphere in n dimensions, and it has an ON symmetry. And then we are going to couple a magnetic field, one of the constant charges, and then put this magnetic field very, very large, squashing the system in 2 dimensions, and then it's integrable and we can solve it. It's a quantum field theory, so I could take this Lagrangian and calculate the free energy density in perturbation theory. If I do so, I would use dimensional regularization. I have to renormalize the Baire coupling. I have to introduce the dynamically generated scale. And finally, I can write the free energy density in terms of a running coupling, which involves this dynamically generated scale and the magnetic field. And this running coupling very nicely resums all higher logarithms and log-log terms in the magnetic field. So this is a perturbative expansion based on the Lagrangian. One can do the calculation, 1 loop, 2 loop, 3 loop. We did it with Grisha some time ago. But of course, based on the Lagrangian, we couldn't go higher orders. But this theory is integrable. So using integrability, we could actually calculate, based on the method of Volin, Dima, Volin, we could calculate 20 terms, 40 terms, 50 terms analytically. Even better, if we do the calculation numerically, we could calculate 1,400 perturbative coefficients up to 4,000 digits. So I would like to teach you that having such an amount of data, you can extract a lot of physical information. In particular, you can extract non-perturbative corrections from this. So let's start with this observable. I know this observable, as I mentioned, 1,400 coefficients. And then, because I know it very precisely, I can really see that they grow like factorial. It's written explicitly here how they grow. Yes. Yes, okay. So they grow like this. So the first lesson I would like to teach you, and I would like to ask you to use your brain a little, so what can we do if we have a perturbative series which is factorially growing? It has a 0 radius of convergence. So the idea is that I will replace with another series when I divide by this factorial grow. So instead of using this chi n as perturbative coefficient, I will divide by n factorial. I make another function. When I divided it, this is called the Borel function. So I'm making a transformation on this function. And this function behaves much nicer because it will have a finite radius of convergence. You can think of this transformation as evaluating the path integral in 2 steps. First, I evaluate the path integral when I fix the value of the action, and this is this Borel function, and then I integrate for all possible actions. So it's a very natural function, and then this basically shows you what is the inverse of that transformation. So I have to integrate that Borel function on the real positive line, and then I can get back my original function. Of course, if I would do it order by order, then I could get the same asymptotic series. So the idea is not to do it order by order, but to take this function, which is on the Borel plane, has a finite radius of convergence, and then do an analytic continuation in a clever way, such that then after the analytic continuation, I could integrate on the real line. Of course, if I have some singularity on the real line, then I got in trouble, but otherwise it's a good method. So to get some naive analytic continuation, I could just use the Padilla approximant. So I approximate this function by a rational function, and I fix this coefficient by comparing the perturbative expansion of the Borel function. Then I got a quite good, actually, analytic continuation. Doing in this particular observable I'm describing, I can realize from the zeros of the denominator of this analytic continuation that there is a cut starting at -1, and there is a pole at 1, and then a cut starting at 2. So this is a kind of typical behavior. And now when I would like to integrate on the real line, I see that there are singularities, so I have to do something. One way is to integrate a bit above, or otherwise I could integrate a bit below. So there is an ambiguity in the inverse of this transformation, and we can see what is this ambiguity. So what is the difference between integrating above and below? And I will see that the magnitude, for example, of this pole is e to the minus 2 over alpha. So it's non-perturbative. So this is one of the messages. If I have an asymptotic series, then necessarily I will have non-perturbative corrections. And then similarly, the cut will also contribute to this ambiguity. So the next slide explains a bit what we should do in general. And then I think it's kind of simple to follow, and I ask you to follow it because I think it gives a nice insight. So you have a function, a perturbative expansion, with factorially growing coefficient. We make this Borel transformation by dividing the factorial, and then we analyze this Borel function, and I'm to extract the analytic structure of this Borel function, it's enough to know the asymptotic behavior of your perturbative series. So if the asymptotic behavior, it looks like this, that we already divided by the n factorial, so the leading behavior is a constant, like p plus, say. And then if we could calculate the 1 over n correction and the 1 over n times n minus 1 correction, and let's assume I could calculate all of them and also suppress terms like 2 to the minus n times similar constant 1 over n times n minus 1, then I can easily resum by definition how this function was defined. I could make the resummation. And if I resum, for example, the constant term, it's a constant times t to the n, it's easy, it's 1 over 1 minus t. So it's a pole at 1. Similarly, if I resum this minus 1 to the m times p minus, then I will have a pole at minus 1. If I resum the 1 over n correction, it will give me a logarithm. If I resum the next one, it will give a term multiplying this logarithm with p minus, written here. So if I can calculate if all these coefficients here, they will actually lead to the function which multiplies this logarithmic cut. So the function, the analytical structure of the function of the Borel plane is determined by the asymptotics. When I do this inverse transformation, integrating on the real line, then I will get some imaginary part of the function, and that imaginary part, that ambiguity, is completely determined in terms of the asymptotic behavior. So the non-perturbative corrections encoded into the asymptotic behavior of the perturbative series. So this is the message. Doing the calculation in our data, we had this 1,400 coefficient, we can actually could fix with very precisely this asymptotic coefficient. Once we fix the asymptotic coefficient so precisely, we could make the inverse Borel transform, and then we found an imaginary part, which was not expected from the result, So in order to have a real, well-defined result, we have to subtract this imaginary part. But the problem is that in this imaginary part, what we subtracted, and we calculated from the asymptotics here, then this is also a series which is asymptotics. So the final result was the perturbative part, and these exponentially suppressed corrections, what we calculated from the asymptotics, but they are also asymptotics, so we have to compensate also them, Borel sum them. Saying it differently, when we calculate the analytic structure, we found some logarithmic cuts, and the function multiplying these logarithmic cuts, but that functions also had logarithmic cuts. So we had the logarithm of the logarithm, so we have to compensate all of them, and there is this very nice theory of resurgence, how to do it. And if you do so, then, for example, out of this 1,400 coefficient, we could calculate the asymptotic behavior of the asymptotic coefficients, and we could compensate our original function, and we could compare the numerical solution of this free energy calculation, and we could see that we completely described the function up to the second non-perturbative order. So let me summarize what is the structural result for this free energy. We had the perturbative series. This perturbative series was asymptotics. Because it was asymptotics, there are non-perturbative corrections. From the asymptotical behavior, we calculated this non-perturbative correction. But because this is also asymptotics, there are higher non-perturbative corrections. So in principle, we believe that it is described by a trans series, a perturbative series, and many, many non-perturbative corrections, infinitely many, and each non-perturbative correction has actually a perturbative series, and they are related to each other in a very intrinsic way, such that the asymptotic behavior of this perturbative or higher perturbative series will determine higher non-perturbative corrections. So the question, is it possible to describe all these perturbative series and non-perturbative corrections? And the answer is yes. So in this ON model, we managed to actually find the basis of functions with which we could describe all non-perturbative corrections. Any higher correction could be described by some path, and then depending on the size of this path, if it were higher, then we got a higher order non-perturbative corrections. So this completed this theory in this ON model. And we would like to do something in n equals 4 super Youngness. Of course, we would like to do it in QCD. But in QCD, we cannot do calculations. Even the Lagrangian of the standard model is filling an A4 page. So we will switch to n equals 4 super Young-Mills, which is just one line. It has 1 gauge bosons, 8 fermions, 6 scalars. Here we can also do perturbation theory. Of course, if it's just perturbation theory, it's not much better than QCD. What is nice about this theory, that this is actually integrable. So we have the gauge theory description, which is a conformal field theory. So we could calculate like 2-point function. We take this, say, complex combination of the scalar, and then we can calculate the 2-point function of this operator. This is the spectral problem, and we could expand it perturbatively. If we expand perturbatively, these are these red curves. Yeah, wrong. So here I'm presenting some observable, like a scaling dimension, expanded perturbatively from the gauge theory. Of course, it cannot go to very, very high coupling. But since we have this ADS-CFT correspondence that n equals 4 super Young-Mills is dual to string theory, type 2B string theory on ADS5 cos S5, we could also expand the same observable, the energies of the spring states, in string theory. Then we will get a large coupling expansion, shown green here. This is also an expansion. And the conjecture is that these two theories are equivalent, but it's hard to compare these two expansions, actually. So the way we can prove, sort of, that this duality is valid, that behind this model, actually this is the Wirth string theory, is integrable. So we can use integrable techniques to calculate the spectrum exactly. This is done in terms of some thermodynamic Bethe-Ansatz equation or quantum spectral curve, and that provides this blue curve, which interpolates between the two, and by expanding in weak coupling or strong coupling, we can see they agree with the string theory or gauge theory. So this is the spectral problem. Today I would like to talk about another observable in N equals 4 super Young, which is a 4-point function. So the 4-point function of half BPS operators. So the operators I would like to take like trace x to the k, and then these other two operators. And I would like to calculate this 4-point function. I would like to calculate this 4-point function in the limit when the size of these operators are large. I'm doing this because there are some perturbative correction which goes between the operators in this worksheet. They are connecting the operators, and if I'm sending this k to infinity, then I'm killing those perturbative diagrams which would connect the top, the face, I can cut this worksheet into two parts, a front octagon and the back octagon, and I'm killing those perturbative terms which wrap between these two, which connect these two. So this 4-point function in the limit, when k goes to infinity, it actually factorizes into the product of the same object, what is called the octagon. So I would like to calculate this octagon. Perturbatively, it can be calculated at weak coupling and can be written just as in terms of these ladder integrals. At strong coupling, we could calculate it by determining the minimal surface with the boundary condition of this operator, evaluating the minimal surface, and then summing up the small fluctuations. And of course, I would like to interpolate between these two with some integrable description. And the integrable description is that if I take just this one octagon, the front, if I cut half, the front picture, and I can cut it into two hexagons, and in the integrable description, I have to insert a complete system of states between this hexagon 2-point function. I have to sum them up. And it's possible to do. The result is a determinant of an infinite matrix. The matrix element of this infinite matrix can be written in terms of this form. So this is it looks like a matrix element of the chi function between odd Bessel functions. So this is how this KNM is defined. And then the function in what appears in the octagon, it's written here. So it's some function of the cross ratios. We are in a conformal field theory. This is a very nice result. This is valid for any coupling, and it interpolates between the weak coupling result and the strong coupling result. What is interesting, that just slightly generalizing this expression, not to have only odd Bessel functions, but also even Bessel functions, one can actually introduce an integral kernel to understand this matrix element as the matrix element of the integral kernel between these Bessel functions. This is called the Bessel kernel. It's written here in terms of Bessel function, and multiplied with this chi, and this chi is called the symbol of this Bessel kernel. So what is kind of interesting and miraculous, I talked about only the octagon, but there are many, many observables which can be written exactly the same form, just with a different symbol function. For example, the Tracy-Vidon distribution corresponds to the same Bessel kernel, where the symbol function is just the theta function, shown black here in the corner. The expectation value of the circular V-zone loop in n equals 4 super Young-Mills can be also written like this determinant, but the symbol is like 4 over x squared, and then also flux tube correlators, Kasparov-Malus dimensions, and even n equals 4 super Young-Mills theories, some free energy or Wilson loops can be written into the same infinite determinant form, but with a different symbol. So what we try to do, we try to develop a method to expand this determinant observable as strong coupling. You can think of these determinant observables as a generalization of this Tracy-Widom distribution from this hard cutoff to a smoother cutoff. So what we would like to do, we would like to make a strong coupling expansion. This is actually an interesting mathematical problem. And mathematicians started to solve this problem almost 100 years ago by Segue and Poya and Katz and other people. But recently there was a very nice breakthrough by Andrei Belitsky and Grisha Korchemsky. They could manage to calculate the perturbative correction, shown FLG here, in a very nice way. And the way they did, they introduced the resolvent, and they found a very nice differential equation this resolvent should satisfy. Combining this differential equation with another equation, how the resolvent was actually related to this observable f, more like the derivative of this f. They related in two different ways. We just came up with some parametrization, and then this differential equation with this back coupling basically determined all these coefficients. So all perturbative coefficients can be determined in terms of moments of the symbol of the kernel. So this is a very general approach. It works for all determinants, all symbols, and then the strong coupling expansion explicitly written in terms of these moments of the symbol, written in this way here. What is interesting that the octagon at a special point y equals 0, psi equals 0 was actually related to the localization result by g minus g. Yeah, my time is up. So what we figured out recently, that how to extend this perturbative calculation to the non-perturbative level. So we could, from the perturbative coefficient, we had already many perturbative coefficients, we could calculate the non-perturbative coefficient. And the location of this non-perturbative coefficient was related to zeros of the kernel function. We calculated it explicitly, and we checked that we have a similar asymptotic relation between the perturbative coefficient and the non-perturbative correction. And we compared we checked numerically that this is really the right solution. So I hope I could convince you that if you have an asymptotic series, then necessarily you have non-perturbative corrections. You can actually calculate these non-perturbative corrections from the perturbative series. And then we use this machinery in one model, the O4 model. Actually, we solved it exactly. And then we started to solve also in this n equals 4 super Young-Mills. We don't have the complete solution yet. It's already interesting that we found this non-perturbative correction. It's very interesting to which this non-perturbative corrections belongs to, what is the interpretation, like worksheet and instantons. And it would be nice to investigate this question, generalize for other observables, and so on. So maybe I stop here. Thank you.
Questions?
I was going to ask about these worldsheet instantons. Do you have some idea of what they would be, how to construct them, or?
I don't. I don't, but there was one paper, I think, about this recently when they analyzed some integrated correlators, and then at the strong coupling expansion of the integrated correlators, they also found non-perturbative corrections, and then they went a bit beyond, then they investigated, but I haven't checked yet. Yeah, but there are some literature, and then we should follow this.
But do you expect to be able to explicitly construct solutions that correspond to this? Or
This would be very nice, actually, to explicitly construct the solutions, then compare the instanton action with the order of the non-perturbative correction, or even more, to analyze small fluctuations around the instanton, and it should give exactly the corrections we calculate.
At some point, you had a picture of something that looked like lattice paths.
Like what?
Like lattice paths.
Yes.
Do they play
Yes,
some
yes,
role?
yes, yes,
Could you
yes.
comment a bit on that?
Yeah, sure.
Yeah, here.
So this was the generic solution for this full trans series in the O4 model. So I'm saying that this full trans series, the perturbative series, and then all non-perturbative correction can be described completely in this basic function, which I call A&M. We could calculate perturbatively this A&M function for any n to high orders. And then the final result can be interpreted like the perturbative coefficient I'm just calculating one particular observable, which is called A11, actually it's the member of that basis, which is just connecting one to one. And then we found that the first non-perturbative correction can be described, say, this simpler path. So here, maybe I can show. Yes. Yeah. So, yeah, the simplest perturbative correction, maybe I just read. So it's A1 minus 2, A minus 2, 1. So this is the leading perturbative correction, okay? And then you can interpret as a path starting from 1, going to minus 2, and then back to 1. And the next perturbative, non-perturbative correction, it has two terms. You go from 1 to minus 2, minus to 1, and then also from 1 to minus 4 and so on. But in general, for a generic non-perturbative correction, you have to take a path which starts from 1 and arrives at 1 and goes through those points which are actually determined by the, in this Wiener-Hopf solution, by the kernel of the Wiener-Hopf function. So each path contributes to a non-perturbative correction. And then to which order it contributes, it's related to the length of the path. Yeah.
Yeah.
Thank you. So this determinant representation is suggestive of some free fermion representation, some spectral determinant perhaps. Is there a way to identify what would be the Hamiltonian in which those fermions are living?
I don't know, but I think this original derivation by Kostov, Petkova, and Serban, it's used a kind of fermionization of the calculation. Yeah. But in general, I don't know. So I would say maybe it's related to some localization. And then
I mean, this Tracy-Widom distribution arises in the statistics of largest eigenvalue of some matrix models, and I think there is some free fermion picture appearing there, so maybe it can be carried over to this system.
Mm-hmm. Yeah, so this Tracy-Widom I was referring to with the Bessel kernel, it's related to the Gauss ensemble in the eigenvalue distribution near the edge, indeed.
Yeah, right.
Yes. Yes, so you are saying that this determinant can be fermionized in this case, yes, and then I'm just telling you this octagon was also kind of fermionized, but I don't know about the other observables, but maybe they can be also fermionized. Maybe that would be a way actually to deriving observables in the same determinant form. So one message is if you can bring your observable into this determinant form, then this is the way to make an expansion. Right. Yeah, non-perturbative expansion. Yeah.
Very well. Then, in view of time, let's thank Zoltan again.
I have a choice. I will try this.
Okay.
And
it's
this.
Important that you speak.
It's important that I speak into the microphone. Okay.
And
just speak.
So if you want to use the pointer, this works like a gyroscope. So it's better if you extend. You can point wherever you want.
I see. Okay, but my brain has to match.
It's very sensitive.
Mm-hmm.
But if you do this, maybe
it's easier. Okay, and then that's forwards and backwards.
Okay, so our next speaker is Ben Hoare, and he will tell us about integrable sigma models and the string worldsheet.
That's great. Thank you very much. So let me start by thanking the organizers. It's a great pleasure to be here, my first time in Padova. Yeah, so what I want to tell you about today is some work that's been going on, I guess, over the last 20 or more years, depending on how you count, on these integrable sigma models and the string worldsheet. And in particular, much of what I say, this is my perspective on 20 plus years of work, and many people were involved in this. I haven't included citations because they would probably just fill up the slides. So please forgive me for that. I'm very happy to provide references for anyone who is interested. Okay, so I'm going to start with possibly the slide with the least content in this conference. That's our starting point. So we're considering closed strings moving on curved spacetimes. And in very simple examples, if we consider a string moving on a sphere, we can rotate the sphere, and this system will have a global SO3 symmetry. But the dynamics can also be constrained by infinitely many hidden symmetries, and these act non-trivially on the string, and in this case we say that we have an integrable sigma model. So this is the topic of the talk. So let's see if this works. So this is obviously the string moving in target space, and then we have this description in terms of a cylindrical worldsheet, and then a two-dimensional theory living on that worldsheet, and that is going to be this integrable sigma model. So just let me give a little bit of motivation. Why am I interested in integrability? So as I've already said, there's a large hidden symmetry at the classical and quantum level. We've heard some of this before already, but it gives us access to all values of the coupling. It allows us to conjecture exact results that can be precision tested. And something that will come up again and again is this idea of controlled deformations or dualities. But by controlled, what I mean is you do a deformation or a duality that preserves some symmetry or some property that you want, and in this case that will be integrability. So why string theory? Well, as we've heard many times, it's a theory of quantum gravity, one of the theories of quantum gravity that we have the best control over, and it also gives us insights into gauge theory through gauge gravity duality. And finally, why integrability in string theory? So it actually gives us a new approach to solve strings in non-trivial backgrounds. If we have Ramond-Ramond fluxes, then typical worldsheet CFT methods are not easily applicable. And then moreover, it actually provides us lessons for solving integrable sigma models more generally, and these have applications beyond string and gauge theory. So I'm going to start probably about 2002, 2003, and just recap a bit the methods that we use to study integrable worldsheet sigma models. So we're starting from a free closed string propagating in a curved spacetime, and the sigma model on the the sigma model on the cylinder is classically integrable. It has this infinitely many hidden symmetries. And these are encoded in a lax connection. No, that one. There we go. L, and it depends on a spectral parameter, an auxiliary spectral parameter Z, which is valued in C. And from this lax connection, we can construct which is the path ordered exponential of the lax around this curve. Nope, this is not working. Around this curve, around the world sheet. And by expanding the trace of this monodromy, it's easy to show that it's conserved in time, and by expanding this in powers of the spectral parameter, we construct infinitely many conserved quantities. So then the story goes on, and you fix a uniform light cone gauge. So this is a type of gauge fixing on the string world sheet where we eliminate all unphysical degrees of freedom. So generalization of the usual light cone gauge of flat space to curved space. And we expand around a point-like string solution. What we end up with is a two-dimensional integrable field theory on a cylinder with 8 bosonic and 8 fermionic degrees of freedom. That's our usual degrees of freedom of world sheet string theory. If we have curved spacetime, then we often end up with interactions that are not Lorentz invariant. And the global symmetry of our model will be broken to a subgroup depending on the particular light cone gauge that we picked. So then, just to rapidly move through probably about 5-10 years worth of work, the story goes that you decompactified the string world sheet, so you're now considering your theory on a plane. You consider excitations, and you scatter these excitations, and using integrability, you can conjecture, and various other physical properties, you can conjecture the exact dispersion relation in the S matrix. In particular, you can use the Yang-Baxter equation, which is basically saying your multi-particle scattering factorizes into two-particle processes. And once you have this S matrix, you can develop and use the integrability toolkit. So there's various methods which we've heard mentioned briefly, asymptotic beta ansatz, thermodynamic beta ansatz, quantum spectral curve, so on, to recompactify the string and conjecture the closed string energy spectrum. So we've already kind of heard hinted that I'm only telling you one half of the story. I'm only telling you about the strings on ADS space, and one of the motivations for studying this was the ADS-CFT correspondence, and in particular the ADS-CFT correspondence is challenging to test or prove. It's a weak-strong duality. Solving strongly coupled conformal field theory is different, and strings on ADS space need to be supported by these background fluxes, which means we can't use these world sheet, or sometimes we can't use these world sheet CFT methods. So integrability provides us with a way forward, and I'm just checking. I think my triangle is the same orientation as Zolli's. We have CFT in the top left, and we have string theory in the top right. In particular, we're in the planar and free limits. So the free string limit corresponds to this planar limit in n equals 4 super Yang-Mills. And we have an underlying integrable system that describes both of these theories. And this triality has sort of led to many remarkable achievements. As I briefly mentioned, it's led to a proposed solution for the spectral problem for all values of the coupling. It's grounded in rigorous string theory and CFT, by which I mean you can precision test this on both sides of a strong and weak coupling. And it's a remarkable new successful application of integrability methods. However, there are some big open questions. I think it's fair to say that ultimately quantum integrability is a conjecture. So we can test this at weak and strong coupling, but in principle, we should prove that these theories are quantum integrable for all values of the coupling. The underlying hidden symmetry is not well understood. So for example, on the CFT side, I didn't really mention this, but the integrability manifests itself in a spin chain, which we did hear about yesterday. And that spin chain is known at small values of the coupling, but it's not known to all orders in the coupling, what this spin chain actually is. And ultimately, it's most successful for the most supersymmetric cases. So I'm mainly going to focus on this last point and ask the question, how do we move away from 32 supercharges? So ADS5S5 is this example of this maximally symmetric background with 32 supercharges, and we want to move away from this. And this is just a selection of kind of approaches that people have been using. Now probably we're in the last decade, a little bit more, to tackle this question. So there's a kind of, I flipped the orientation of my triangle, but there's a kind of, there is a triangle here. We have sort of world sheet deformations and dualities. So this approach is sort of starting from the string sigma model and asking how we can deform or dualize or modify the string sigma model to preserve integrability. In the top right now, we can look at CFTs with less supersymmetry and ask, can we find integrability or the effects of integrability in those theories? A third approach is to start from the integrable structures themselves, this scattering matrix on the world sheet theory of the string, and try to deform that model, or try to deform that itself. Another approach which we heard about yesterday, which I won't mention anymore, is to consider things like defects, orbifolds, and boundaries in your theory. And then the final thing is to try and go down to lower dimensional ADS backgrounds, so ADS4, ADS3. So mainly today I'm going to focus on these two in the top left as you're looking, so the world sheet deformations and dualities and the lower dimensional ADS backgrounds. So let's start with the lower dimensional ADS backgrounds. As we go down in dimension, there's been various classifications that have been carried out, and we find more and more integrable string sigma models with less and less global symmetry. So in particular, if you go down 1 to ADS4, you find ADS4 times CP3. If you go down, one option is ADS3 times S3 times T4, but you could replace the T4 with S3 times S1. There's a moduli space for this theory. You can support it by different fluxes. So new features appear as we go down in dimension, which is appealing. However, also the lack of global symmetry, or the less global symmetry, means that we have less immediate control. We have more objects that we can play with that are invariant under these symmetries. So that's one direction. The other direction is to look at deformations and dualities. And this is a very cartoony sketch of the landscape of deformations and dualities. I'm not going to go into it in detail, but basically there's a kind of myriad of possible ways to deform and dualize, and they break different amounts of symmetry and supersymmetry. And for those of you who are familiar with sort of quantum integrable systems or integrable systems, these deformations include the sort of sigma model avatars, if you like, of Drimfeld twists and quantum group deformations, Q deformations. So this beta gamma deformation is an example of a twist, and these eta and lambda deformations are sort of correspond to Q deformations. And moreover, we can sort of generalize T-duality to non-abelian and Poisson-Lie symmetries. And I guess the message I want to take away is this is a big space of models. So when we put it all together and we go down in dimension and we kind of expand out to all these deformed models, we end up with a kind of really big landscape. And one of the kind of main things that's been kind of achievements over the last few years is kind of understanding this landscape in a more systematic way. So I remember being told probably about 5-10 years ago that which deformations, or asked the question, which deformations should I care about? There's too many of them, I can't study them all. And yeah, it was a very good question, and I think we are slowly starting to pin down which are the interesting cases and sort of understand this landscape and how they are related to each other. So at this point, I have sort of 3 slides of kind of directions / questions that I think are interesting in this landscape and beyond. These aren't sharp questions. I'm very happy to give people sharp questions. There's many of them I would like to answer, but these are sort of areas which I think if someone could say something interesting about these, it would be important. So let me start just with integrable string theories and charting the landscape of and solving integrable string theories. So a kind of question that has received a partial answer is, do we always find consistent string theories? So if we take a model, I'm talking about deforming or dualizing while preserving integrability, that doesn't necessarily guarantee that I preserve Weyl invariance or string theory, or that it gives me a consistent string theory. So there are kind of different aspects to that question. One is whether the theory is Weyl invariant itself, and that question has received has a kind of pretty solid answer. We know when it is and when it isn't. There's another big question, which is that many of these backgrounds end up having singularities, essential singularities in the curvature, and as far as I am aware, it's very unclear how to treat these singularities. So my approach to that question is to look for models that don't have singularities, but there are ideas about how to interpret these singularities themselves. When we deform, when we dualize, we break symmetries. Uniform light-cone gauge fixing relies on having certain symmetries. Can we follow this integrability path of fixing uniform light-cone gauge and constructing the S matrix? How do the symmetries interplay with the S matrix itself? And then can we go on further and apply all this toolkit, this ABA, TBA, quantum spectral curve? So I should say that for different models, some of these questions have been studied, some have not, but there's bits and pieces of kind of information in all these directions, and there's many kind of open questions. And then finally, something that was discussed in Zoli's talk, so can we move beyond free strings? So beyond just the spectrum to correlation functions or even higher genus. There's a whole bunch of special limits that we would like to understand. So one that's received a lot of attention is ADS3S3 T4, where you can support the model just by pure NS&S flux, and how, in that case, you can use normal worldsheet CFT methods, and how the integrability approach maps onto that. Flat space limits, tensionless limits, non-relativistic limits we heard about this morning. There's also a whole bunch of different formalisms. So we have the Green-Schwarz formalism, pure spinor formalism, hybrid formalism, and it's an interesting question how all of these are related. Can turn now to sort of the gauge theory jewels of integrable string theories. So what are the gauge theory jewels of lower dimensional ADS backgrounds? For ADS5 and ADS4, we kind of know it's n equals 4 and ABJM. For ADS3, there are certain points in the moduli space where there are good proposals, but moving away from those related to the symmetric product orbifold, moving away from those points, there's kind of questions to be answered. So that's lower dimensional ADS backgrounds. We can also ask about gauge theory jewels of deformed backgrounds. In this case, there are kind of two approaches. One is to take the spin chain that you get from n equals 4, for example, and try and deform that spin chain. You could also try and deform the n equals 4 Lagrangian itself, and in this case you get sort of non-commutative field theories appearing. And then there's some, I think, very interesting questions about certain limits that you can take in the gauge theory. What is the string theory interpretation of that? And let me just focus on the middle case here. So if you take n equals 4 super mils and you do sort of a twist of this model and you take a maximal deformation limit, so you take your deformation parameter off to infinity, but at the same time you take the Yang-Mills coupling to 0, so you do this double limit, you get a very nice model called the fishnet model, which just has two complex scalars, and is meant to be integrable, or it is integrable. There is a proposed dual for that model called the fish chain, but how you relate that proposed dual, how do you get that proposed dual from string from ADS5 S5 string itself is not clear as far as is not known as far as I'm aware. So, and finally, if we move away a bit from string theory and gauge theory, all of this progress in string theory is actually in integrable string sigma models has actually led to a much better understanding of actually the landscape of integrable field theories in 2 dimensions itself. So different communities have contributed to this, but there's been important contributions from the string side. And there are sort of these new classifications involving higher dimensional gauge theories, something I'll come back to in a second, and affine Godin models. Also important questions about quantization, the relationship between integrability and renormalization, and renormalizability, and how to, and whether you can formulate sort of strongly coupled jewels on the world sheet. Let me, it would also be interesting to look at integrability in more than 2 dimensions, so there's some interesting results in that direction. And then applications beyond mathematical and theoretical physics. So we heard yesterday in the public lecture about various statistical mechanics models. There are a whole bunch of statistical mechanics models that have as part of their description very symmetric sigma models, and it kind of be including supersymmetric sigma models, and it would be interesting to ask all of these deformations we've seen in string theory, do they mean anything, or do they have any counterpart in these statistical mechanics models? So that's my sort of list of directions that I think would be interesting. I just want to finish with 2 things that I've been working on, two directions that I think are interesting, which are related to some of these questions that I've mentioned here. So the first is 4D Chern-Simons. So the landscape of integrable field theories continues to grow. You can try to construct them directly. You can also try to use more general guiding principles. So you can use this ideas of deformations or dualities. But there have been these 2 sort of systematic frameworks or approaches that have been developed, so affine-Godin models and 4D Chern-Simons. I'll briefly explain what 4D Chern-Simons is, but these 2 are very intimately related. In fact, they're sort of, you can think of them as the Lagrangian and Hamiltonian formalisms of the same system. So this is the action of 4D Chern-Simons. It's a 4-dimensional gauge theory. Sigma here is our 2-dimensional world sheet, so that was our cylinder from before. The other 2 dimensions are given by a CP1. And omega, this omega that sits in front of the action, there, well, you can see it, is a given meromorphic 1 form on the CP1. And the field A is a G-valued 1 form on the full 4D space. So to define this theory, it's not actually defined as given. We need to specify what omega is and also specify boundary conditions to make sure the boundary variation vanishes. And then by introducing defects on CP1 and degrees of freedom living on those defects, what we can find is that the theory localizes to give different 2D IFTs. And there are different types of defects. There's what are called order defects. These are quite restrictive. There's disorder defects where we introduce poles and zeros into omega. And then we can also introduce sort of branch cuts that describe models on cosets. So this is a sketch of an example. So I claimed in the previous slide that basically to specify the theory, we specify omega and we specify boundary conditions. That should tell us what our theory is. And for the PCM, this is what omega is. So basically it has 2 simple zeros at plus or minus I, and it has 2 double poles at plus or minus 1. And the boundary conditions are that the gauge field should vanish at the double poles. And in this picture, the ideas of deformations and dualities become very intuitive. So to deform, what we can do is we can move these poles, or we can split these poles, we can move them around. So for example, in this picture, I've split the double pole into 2 simple poles. I've modified the boundary condition, and it's not clear from what I've written, but this boundary condition will reduce back to the PCM boundary condition in the limit where the 2 poles coincide. On the other hand, dualities tend to correspond to changing the boundary conditions, keeping omega fixed and using different boundary conditions. So this example here is basically going from the PCM to its non-abelian T-dual. And what's nice is that if you split the double pole, you can interpret this as taking you from a rational to a trigonometric model. So we map from the plane, from CP1, and we take our 2 poles to the ends of our cylinder, and we're just left with a cylinder with a double pole and 2 simple zeros. And then we can go further, and we can go to elliptic models by gluing the cylinder together. And in principle, as far as I'm aware, there's not much work on this, but we could even go to higher genus Riemann surfaces. So one fun thing you can do is go lift up to even higher dimensions, and you can construct diamonds of integral models. What you find is that 4D IFTs, so what you find is on this bottom left-hand side, we have 4D Chern-Simons and 2D IFT, and you can lift this up to 6D holomorphic Chern-Simons and 4D IFTs. These 4D IFTs are related to self-Joule-Yang-Mills and the Ward conjecture. And even now, after many, many years of people coming up with new integral sigma models, these kind of higher dimensional gauge theory constructions are still giving rise to new field theories and relations between them. So there's still much to explore. And the final thing I want to mention, maybe my last 1 plus epsilon minutes, is the ADS3 times S3 T4 superstring. So this is a very nice example. In particular, it has a direct product symmetry group. So we have 2 copies of PSU 1,1/2. And this direct product structure gives a new freedom. So we can deform copies of the symmetry group independently. And the case where only 1 copy of PSU 112 is deformed is particularly interesting. In particular, half the global symmetry is preserved. So we only deform 1 copy and we leave the other copy alone. So if we just look at the S3 part, what we find is that this, if we do the trigonometric deformation, we find the squashed 3-sphere. So that's sketched here. We have J1 squared plus J2 squared plus J3 squared. And then we just deform one of the legs of the current. And let me not go through all the details, but this model ends up having some very nice properties, including supersymmetry, integrability, Weyl invariance, regular curvature, so no singularity, homogeneous fluxes, and a constant dilaton. And in my mind, it's probably the best candidate to find a sort of Q-deformed version of the ADS-CFT correspondence. And then you can even go further and try to do elliptic deformations, and you find that many of these nice properties carry over. The Weyl invariance, the regular curvature, homogeneous fluxes, and constant dilaton. However, supersymmetry and integrability are still an open question. So with that, I would like to just say thank you for listening, and I'm happy to take any questions. Thank you.
Questions?
So this integrable sigma models, some of which you're talking about, are they stable under RGs or what?
So these are, sorry, yes, these are all stable under 1 loop RG flow. 2 loops is a bit more subtle, but for 1 loop they are all stable under 1 loop RG flow.
It's
and this is, so actually there is a very nice picture of this from 4D Chern-Simons. There is a conjecture that basically, if you have your poles and zeros, you can construct various monodromies of your twist function. And so all of your couplings are essentially contained in your twist function. And you can construct various monodromies, and any monodromies that are encircling poles will be RG invariant, and then monodromies in between zeros have a very simple RG behavior. But there's a sort of it's still conjectural, and I think there is much to be understood there. But there is a kind of indication that this RG from 4D Chern-Simons, or 4D Chern-Simons, may explain this very nice RG property that all of these integral deformations appear to be stable under RG flow.
More questions?
Hi, Ben. I have a question about 4D Chern-Simons theory. What is known about quantum 4D Chern-Simons theory?
Very little. So, in the case that there are no disorder defects, then I think everything is in principle fine. You can quantize. So there are disorder defects essentially correspond to having zeros in your twist function. And when you have zeros in your twist function, in principle, the theory close to those zeros becomes strongly coupled. And then it's very hard to understand anything about quantization. But away from, if you are talking about order defects, then omega does not have any zeros. And then in principle, you can just use perturbation theory. You can quantize this model, and much has been understood, going back to Costello and Yamazaki and Witten in their papers.
So can you see RTT relation for the lax matrix?
Yeah, so in these cases, these cases correspond to having an ultra-local Poisson bracket, and then
ultra-local.
Oh, yeah. So the order defects corresponds to having ultra-local.
So it's basically a spin chain.
So yeah, and certain very nice sigma models,
Right.
well, which are related. But yeah. So yes. So I'm not. Yes. So 4D Chern-Simons with disorder defects is the more interesting case, and understanding quantization there is, it's a big open problem. I don't necessarily think it no, that's not fair. I think it could buy you something in terms of 4D Chern-Simons. I reserve my judgment, but it waits to be seen.
And I suppose 6D Chern-Simons even worse.
Worse. Actually, weirdly better. Some of the zeros. Well, it turns out that some of the zeros that come in the 4D Chern-Simons, some of the zeros that are appearing in the 4D Chern-Simons twist function are not there in the 6D. They come from the symmetry reduction.
Mm-hmm.
So weirdly, actually, you can say more about the quantization of the 6D holomorphic Chern-Simons than about the 4D Chern-Simons. And there is a poster of Lewis where he can probably tell you more about this than I can. But there is a symmetry reduction in the way. And so I don't think it teaches you necessarily about the quantization of the 4D Chern-Simons and the 2D IFT. So, yeah.
Okay, thanks.
I have a question. If you start from maximally supersymmetric Yang-Mills theory, that's 5 cross 5. So we know there is certain quantity in this theory could be computed using localization.
Mm-hmm.
So what happens if you start introducing deformation? What kind of deformation are consistent with localization, and if it's so, what can you compute in those theories?
That's a great question. I can't think of anything in that, any work that's been done in that direction. Please correct me if I'm wrong, but it's a very interesting question. I've not thought about it.
A naive question. 6D Chern-Simons is 3D Chern-Simons multiplied by 3 form, or 5D Chern-Simons multiplied by 1 form?
Yeah, so sorry, I've been a bit sloppy. So it's 6D holomorphic Chern-Simons, which is basically a much in the same, well, if I go back to this action, in this case, you have a gauge field, a 3,3, so in this, when you lift to 6 dimensions, the omega becomes a 3,0 form, and then you have the normal holomorphic Chern-Simons 3 form, or anti-holomorphic Chern-Simons 3 form, pairing it to get the full.
The model is 1 form multiplied by Chern-Simons, 5-dimensional Chern-Simons. It is not so interesting.
I wouldn't say that. It's something I've not thought about, so I don't have anything to say, but it could be interesting.
Yeah, but just to know if you are aware of, according to this work of William Williams, who claim to prove one loop exact beta functions for the Chern-Simons sector, I'm not sure. Do you know how much of this one loop exact arguments can translate to this holomorphic Chern-Simons theory or supersymmetric ones, like in 2D? So these are like 2 different sectors.
So you say there's a proof in the case of...
That's what they claim.
In case of disorder defects or in the case of order?
I think even without defects.
Oh, okay.
Like in regular CS theory, yeah.
Say again?
In regular Chern-Simons.
In regular Chern-Simons, not
this
in...
is what Will and Williams, they talk about.
Not in 4D
yeah,
Chern-Simons.
yeah,
Sorry, okay. And then your question, okay.
And the point is how much of this, if you know, can translate to holomorphic sector, holomorphic Chern-Simons.
Well, seeing as I'm not aware of that result, I can't, I'm not sure, but I would certainly be interested to discuss. Yeah.
Any other question? Then let's thank Ben again.
Before we set you free, actually 3 announcements for 3 different categories of people. One is for everybody, the other is for people who are presenting the poster, and the last one is for members of the core group. You know who you are. For everybody, we have a dinner tonight, 7:30, at Café Pedrocchi. It's on the website, there is a map, it's very close to here. So enjoy, take a nice walk, relax, and then see you there at 7:30. It will be signposted by our banner, the yellow banner, so you will find it easily. For the core group, we meet also at the Café Pedrocchi, but we meet at 5:45 there, in the green room for our core group meeting. If you go there, you ask for the green room or Sala Verde, they will direct you to the room, okay? And then for people presenting the posters, tomorrow is probably going to rain, already tonight is probably going to rain. Therefore, the posters and also the catering will be moved to another place. And you have to move the posters yourself. It's just across the courtyard in a very beautiful room, which is called the Teatro Vesaliano. And the way will be pointed by our hostess that will take you there. She will show you where to put the posters, but you have to move the posters yourself. The idea is that if you are presenting a poster, you try to move your own poster. Maybe you bend up with another person. Each board has 4 posters, so at least 1 or 2 of you should be here. So please do that now before leaving. Okay, that would be all, unless you have questions about practicalities, in which case tell me now. Is it clear? Yes? No, I think that this place closes in like half an hour, just a time to set things up. In fact, you can find a nice cafe and sit there. I think it's a simpler solution to your nice terrace, get something to drink and relax. Simpler solution to your problem. Well, most cafes do have internet. All right, anything else? Enjoy the rest of the afternoon, see you at dinner.